The future of Agentic RAG, 2026 and beyond. Agentic Retrieval-Augmented Generation, RAG, is poised for exponential growth beyond 2026, driven by advancements in AI agent sophistication, knowledge graph technologies, and real-time data integration. We foresee a shift from static, query-based RAG to dynamic, proactive systems that anticipate user needs and evolve alongside changing information landscapes. Key trends shaping the future. Hyper-personalized information retrieval, moving beyond simple keyword matching. Agentic RAG will leverage deep user profiles, contextual understanding, and behavioral analysis to deliver highly relevant and personalized information experiences. Imagine a research assistant that automatically identifies and surfaces crucial insights before you even know you need them. Autonomous knowledge discovery and curation. Agents will proactively explore and synthesize information from diverse sources, including unstructured data, real-time feeds, and proprietary databases. They'll automatically curate and update knowledge graphs, ensuring the RAG system remains accurate and up-to-date. Explainable and trustworthy AI. Transparency is paramount. Future agentic RAG systems will provide clear provenance for retrieved information, explaining the reasoning behind their recommendations and allowing users to assess the credibility of the sources. Seamless integration with real-world workflows. Agentic RAG will be embedded into existing business applications and collaborative environments. Imagine instant access to relevant knowledge within your CRM, project management tools, or even during video conferences, leading to faster decision-making and improved productivity. Multimodal RAG, integrating information from various modalities like text, images, audio, and video will unlock new possibilities. Imagine an agent that can analyze a customer support ticket, identify the product based on images, and suggest relevant troubleshooting steps with video tutorials. Ethical considerations and bias mitigation. As agentic RAG becomes more powerful, addressing ethical concerns around bias, fairness, and privacy will be crucial. We anticipate robust frameworks and algorithms to mitigate potential biases in data and ensure responsible deployment. Impact on industries. The advancements in agentic RAG will revolutionize various industries, including healthcare, empowering doctors with real-time access to the latest medical research and patient data to improve diagnosis and treatment. Finance, enabling financial analysts to quickly identify market trends and make informed investment decisions. Education, personalizing learning experiences for students and providing educators with tools to create engaging and effective curricula. Legal, assisting lawyers with legal research, contract review, and litigation support. Our vision. We are committed to pushing the boundaries of agentic RAG to create intelligent systems that empower individuals and organizations to access, understand, and utilize knowledge more effectively than ever before. By focusing on innovation, collaboration, and ethical considerations, we aim to shape a future where information is readily available, easily accessible, and ultimately contributes to a more informed and productive world. Revolutionizing knowledge retrieval, agentic RAG. Beyond traditional RAG, intelligence and autonomy. Traditional retrieval-augmented generation, RAG, systems excel at enhancing large language models, LLMs, with external knowledge. However, they often lack the sophisticated decision-making and iterative refinement needed for complex information needs. Agentic RAG takes RAG to the next level by empowering RAG systems with agentic capabilities. Agentic RAG leverages the power of autonomous agents to orchestrate the retrieval and generation process. Instead of a single, static retrieval step, an agentic RAG system can formulate complex queries, break down broad information requests into a series of targeted questions. Select optimal retrieval strategies, dynamically choose the best retrieval methods, example semantic search, keyword search, graph traversal, based on the query and available knowledge sources. Iteratively refine retrieval, analyze retrieved documents and adjust subsequent queries to focus on relevant information, overcome ambiguity, and explore related topics. Reason over retrieved information, synthesize and analyze information from multiple sources to identify patterns, contradictions, and insights. Generate comprehensive and nuanced answers, produce more informative, accurate, and contextually relevant responses. Key advantages of agentic RAG. Improved accuracy and relevance, reduces hallucination and increases the factual grounding of LLM outputs. Enhanced complexity handling, enables RAG systems to address more intricate and multifaceted queries. Increased adaptability, adapts to different data sources and information domains. Discovery of novel insights, facilitates the identification of connections and patterns within the knowledge base that might be missed by traditional RAG. Reduced reliance on fine-tuning, leverages existing knowledge bases more effectively, reducing the need for extensive model retraining. Our approach to agentic RAG. We are developing innovative agentic RAG solutions tailored to specific business needs. Our approach involves custom agent design, crafting specialized agents with specific roles and capabilities tailored to the target knowledge domain. Advanced retrieval techniques, implementing a diverse range of retrieval methods, including semantic search, graph databases, and knowledge graphs. Reasoning and inference engines, integrating reasoning engines to facilitate complex reasoning and inference over retrieved information. Rigorous evaluation and optimization, continuously evaluating and optimizing agent performance to ensure accuracy, relevance, and efficiency. Ready to transform your knowledge retrieval? Contact us to learn how agentic RAG can revolutionize your knowledge retrieval processes and unlock new insights from your data. Contact us. Moving from standard RAG to agentic workflows. Traditional retrieval-augmented generation, RAG, systems excel at retrieving relevant information and using it to answer questions or complete tasks. However, they often fall short when faced with complex, multi-step processes requiring planning, reasoning, and tool utilization. Agentic workflows represent the next evolution, offering a more dynamic and sophisticated approach. Key differences and advantages. Planning and decomposition. Unlike standard RAG, agentic workflows can break down complex tasks into smaller, manageable sub-goals, creating a plan of action. Tool utilization. Agents can access and utilize a variety of tools, example search engines, calculators, APIs, to gather information, perform calculations, and execute actions. Iterative improvement. Agents can evaluate their progress, identify areas for improvement, and adjust their approach dynamically, leading to more accurate and comprehensive results. Reasoning and inference. Agentic workflows incorporate reasoning capabilities, enabling them to draw inferences, synthesize information from multiple sources, and provide more nuanced answers. Memory and context management. Agents maintain a memory of past interactions and actions, allowing them to build context and make more informed decisions over time. Use cases for agentic workflows. Agentic workflows are particularly well suited for complex question answering, answering questions that require gathering information from multiple sources, performing calculations, and synthesizing results. Automated research and report generation, conducting in-depth research, identifying key trends, and generating comprehensive reports. Content creation and editing, generating original content, editing existing content, and optimizing it for specific audiences. Personalized recommendations, providing personalized recommendations based on user preferences, past behavior, and real-time data. Workflow automation, automating complex business processes that require human-like reasoning and decision-making. Considerations for implementation. Transitioning to agentic workflows requires careful consideration of factors such as agent design and architecture, choosing the appropriate agent architecture, example React, AutoGen, and designing agents with specific goals and capabilities. Tool integration, selecting and integrating the necessary tools to enable agents to perform their tasks effectively. Evaluation and monitoring, establishing metrics to evaluate agent performance and monitor their progress over time. Cost optimization, managing the computational costs associated with running agentic workflows. Security and privacy, ensuring the security and privacy of data accessed and processed by agents. We can help you navigate the transition from standard RAG to agentic workflows and unlock the full potential of AI-powered automation. Contact us to learn more. How autonomous agents are solving the hallucination problem in RAG. Retrieval-Augmented Generation, RAG, has emerged as a powerful paradigm for building language models that can access and reason over external knowledge. However, a significant challenge in RAG systems is the phenomenon of hallucination, where the model generates content that is factually incorrect or unsupported by the retrieved context. Autonomous agents are offering innovative solutions to mitigate hallucination in RAG through several key strategies. Iterative retrieval and refinement. Unlike traditional RAG pipelines that perform retrieval once, autonomous agents can iteratively retrieve information, evaluate its relevance and accuracy, and refine their queries based on previous results. This allows them to probe for more reliable sources and confirm information from multiple perspectives, reducing reliance on potentially flawed or biased initial retrievals. Fact verification and source attribution. Autonomous agents can be programmed to explicitly verify the factual claims made by the language model against the retrieved context. They can identify the specific source passages that support each statement and flag any claims lacking sufficient evidence. This enhances transparency and accountability, making it easier to identify and correct hallucinations. Multi-hop reasoning and knowledge graph integration. Hallucinations often occur when complex reasoning is required, and the retrieved context lacks explicit answers. Autonomous agents can perform multi-hop reasoning, chaining together multiple pieces of information from different sources to infer answers. Integrating knowledge graphs allows agents to leverage structured knowledge to validate relationships and infer missing information, further reducing the likelihood of generating unsupported claims. Self-criticism and error correction. Advanced autonomous agents can be equipped with self-criticism capabilities. After generating a response, the agent can analyze its own output, identify potential inaccuracies, and revise the content based on the retrieved context. This iterative self-improvement process helps to fine-tune the generation process and minimize hallucinations. Agent coordination and collaboration. Multiple autonomous agents, each specialized in a specific task, example retrieval, fact verification, generation, can collaborate to produce more reliable and accurate responses. This distributed approach leverages the strengths of each agent, leading to a more robust and less hallucination-prone RAG system. For example, one agent retrieves, another verifies, and a third generates based on the verified information. By incorporating these techniques, autonomous agents are paving the way for more trustworthy and reliable RAG systems, significantly reducing the incidence of hallucinations and enabling language models to leverage external knowledge with greater accuracy and confidence. This opens up new possibilities for building AI applications that require factual correctness and transparency. Agentic Retrieval-Augmented Generation, RAG. Agentic Retrieval-Augmented Generation, RAG, represents a paradigm shift in generative AI, moving beyond simple prompt and generation workflows to a more dynamic and intelligent process. This approach integrates the strengths of both retrieval-augmented generation and autonomous agents, resulting in systems that are not only better informed but also more proactive and adaptable. Key concepts. Retrieval-augmented generation, RAG augments the knowledge of large language models, LLMs, by retrieving relevant information from external knowledge sources, example document databases, knowledge graphs, and incorporating it into the prompt before generation. This allows LLMs to generate more accurate, up-to-date, and contextually relevant responses. Autonomous agents, AI systems capable of perceiving their environment, making decisions, and taking actions to achieve specific goals. In the context of RAG, agents can orchestrate the retrieval process, evaluate retrieved information, and refine generation strategies. How Agentic RAG works. Goal definition, the user provides a query or task. Agent planning, an agent analyzes the query and formulates a plan, defining the steps required to retrieve relevant information and generate a suitable response. This might involve breaking down complex queries into smaller subqueries. Knowledge retrieval, the agent utilizes retrieval mechanisms, example semantic search, keyword search, to access and extract relevant information from external knowledge sources. This step can involve multiple rounds of retrieval based on the agent's evolving understanding of the query. Knowledge evaluation and filtering, the agent assesses the quality and relevance of the retrieved information, filtering out irrelevant or unreliable sources. This is crucial for preventing the generation of misleading or incorrect responses. Response generation, the LLM generates a response based on the original query, the agent's plan, and the filtered retrieved information. The agent can guide the LLM's generation process to ensure accuracy, coherence, and adherence to the desired format. Response refinement. Optional. The agent may further refine the generated response based on additional analysis or feedback, improving its clarity, completeness, or style. Benefits of Agentic RAG. Improved accuracy and factuality. By grounding generation in external knowledge, Agentic RAG reduces hallucinations and ensures that responses are based on verifiable information. Enhanced contextual understanding. Agents can analyze complex queries and retrieve relevant information from diverse sources, leading to more nuanced and insightful responses. Increased adaptability. Agents can adapt their retrieval and generation strategies based on the specific query and available knowledge, enabling them to handle a wider range of tasks. Reduced reliance on LLM pre-training. Agentic RAG allows LLMs to leverage external knowledge, reducing the need for extensive pre-training on specific domains. Explainability and traceability. The agent's planning and retrieval processes provide a transparent and traceable audit trail, making it easier to understand why a particular response was generated. Applications. Question answering systems, providing more accurate and comprehensive answers to complex questions. Content creation, generating high-quality content that is both informative and engaging. Code generation, assisting developers in writing code by providing relevant documentation and examples. Data analysis and reporting, automating the process of extracting insights from data and generating reports. Customer support, providing intelligent and personalized customer support experiences. Agentic RAG is a rapidly evolving field with significant potential to transform the way we interact with AI. By combining the power of retrieval, generation, and autonomous agents, this approach paves the way for more intelligent, reliable, and adaptable AI systems. Why your current RAG pipeline needs an agentic upgrade. While Retrieval-Augmented Generation, RAG, pipelines have revolutionized how we interact with knowledge bases, their limitations are becoming increasingly apparent as applications demand greater sophistication and accuracy. A standard RAG pipeline often struggles with complex queries, multi-hop reasoning, and dynamic environments. This is where an agentic upgrade offers a significant advantage. Common RAG pipeline limitations. Limited reasoning capacity. Traditional RAG pipelines primarily focus on retrieving relevant documents based on keyword similarity. They lack the ability to perform complex reasoning, synthesize information from multiple sources, or draw inferences. Inability to handle multi-turn conversations. Standard RAG pipelines typically treat each user query in isolation. They don't effectively maintain context or leverage previous interactions to refine subsequent responses. Lack of adaptability. Static RAG pipelines struggle to adapt to evolving information or changing user needs. They require manual updates to knowledge bases and retrieval strategies. Poor performance on complex queries. Questions requiring combining information from different document sections or involving multiple steps often lead to inaccurate or incomplete answers. Difficulties in knowledge discovery. RAG pipelines generally only retrieve what is already known and indexed. They are not designed to uncover novel insights or identify gaps in existing knowledge. The Agentic RAG advantage. Agentic RAG pipelines overcome these limitations by incorporating intelligent agents that can plan, reason, and execute complex tasks. These agents orchestrate the retrieval, analysis, and generation processes, leading to more accurate, insightful, and adaptable responses. Enhanced reasoning and planning. Agents can break down complex queries into smaller, manageable steps, identify relevant information sources, and synthesize information to formulate comprehensive answers. Improved contextual understanding. Agents maintain conversational context, allowing for more natural and nuanced interactions. They can leverage past exchanges to refine future responses and provide personalized support. Dynamic learning and adaptation. Agentic RAG pipelines can learn from user feedback, adapt to changing information landscapes, and continuously improve their performance over time. Active information gathering. Agents can proactively search for and integrate new information sources, ensuring the RAG pipeline remains up-to-date and relevant. Increased accuracy and reliability. By incorporating verification steps and employing multiple retrieval strategies, agentic RAG pipelines can significantly improve the accuracy and reliability of generated responses. Upgrade your RAG pipeline today. If you're facing the limitations of a traditional RAG pipeline, an agentic upgrade is the key to unlocking its full potential. Contact us to learn how we can help you build a more intelligent, adaptable, and effective knowledge-driven application. The role of tool use in modern agentic RAG architectures. Modern Retrieval-Augmented Generation, RAG, architectures are rapidly evolving from simple retrieval and generation pipelines to sophisticated, agentic systems capable of complex reasoning and task execution. A crucial element driving this evolution is the integration of tool use. In this context, tool refers to any external resource or function that the RAG agent can leverage to enhance its knowledge, capabilities, and overall performance. These tools can range from simple utilities like calculators and web search engines to complex APIs for specialized databases, code execution environments, and even other AI models. Why is tool use important? Tool use addresses several limitations inherent in traditional RAG systems. Overcoming knowledge gaps. While RAG excels at retrieving relevant information from a knowledge base, it's limited to the information it already possesses. Tools like web search engines allow the agent to access real-time information and address knowledge gaps not present in the initial retrieval set. Enabling complex reasoning. Tool use enables agents to perform reasoning steps that would otherwise be impossible. For example, a calculator can be used for numerical reasoning, while a code execution environment allows the agent to test and refine code snippets. Improving accuracy and reliability. By verifying information against external sources or performing calculations using dedicated tools, agents can reduce hallucinations and improve the overall accuracy and reliability of their outputs. Supporting complex tasks. Many real-world tasks require multiple steps involving diverse types of information and reasoning. Tool use allows agents to break down complex tasks into smaller, manageable subtasks, each potentially leveraging a different tool. Examples of tool use in agentic RAG. Here are a few examples of how tool use is being implemented in cutting-edge agentic RAG architectures. Information retrieval and verification. The agent uses a search engine to verify facts retrieved from the knowledge base or to gather additional information on a specific topic. Data analysis and manipulation. The agent utilizes a data analysis tool, example Python interpreter, to process and analyze data retrieved from a database or other data source. Code generation and execution. The agent generates and executes code snippets to solve programming problems or to automate specific tasks. API integration. The agent interacts with external APIs, example Weather API, Finance API, to access real-time data and incorporate it into its responses. Looking ahead. The integration of tool use is a critical step towards building more powerful and versatile agentic RAG systems. As research progresses, we can expect to see even more sophisticated tool use strategies emerge, including adaptive tool selection, agents that can dynamically choose the most appropriate tool for a given task based on its specific requirements. Tool composition and chaining, agents that can combine multiple tools in a sequential or parallel manner to solve complex problems. Tool learning and discovery, agents that can learn to use new tools autonomously and even discover new tools that can enhance their capabilities. By embracing tool use, we can unlock the full potential of RAG architectures and create intelligent agents that are capable of tackling a wide range of real-world challenges. How Agentic RAG navigates complex document collections. Agentic Retrieval-Augmented Generation, RAG, represents a significant advancement in how large language models, LLMs, interact with and derive insights from complex and diverse document collections. Unlike traditional RAG systems, which often struggle with noisy, unstructured, or voluminous data, Agentic RAG leverages a strategic, iterative approach, employing a series of intelligent agents to refine search and enhance content generation. Key capabilities of Agentic RAG in complex document collections. Adaptive retrieval strategies. Instead of relying on a single retrieval method, Agentic RAG employs multiple agents specializing in different search techniques, example keyword search, semantic search, graph-based search. These agents collaborate and adapt their strategies based on the specific query and the characteristics of the document collection. They can intelligently identify relevant documents even when keywords are absent or ambiguous. Document pre-processing and enrichment. Before retrieval, agents can pre-process documents to improve their searchability. This includes tasks like chunking and segmentation, breaking down large documents into smaller, more manageable chunks while preserving contextual information. Entity recognition and annotation, identifying and tagging key entities, people, organizations, locations, to facilitate more targeted searches. Summarization and key phrase extraction, generating concise summaries and extracting key phrases to improve retrieval speed and accuracy. Multi-hop reasoning. Agentic RAG can perform multi-hop reasoning by iteratively retrieving and processing information from multiple documents to answer complex questions that require synthesizing information from disparate sources. This is particularly valuable when dealing with intricate topics spanning multiple documents. Query decomposition and refinement. Complex queries are often broken down into smaller, more focused subqueries. Agents then retrieve information relevant to each subquery and synthesize the results to answer the original question. This iterative process allows for a more thorough and accurate understanding of the query's intent. Verification and fact-checking. To ensure the accuracy and reliability of generated responses, Agentic RAG employs agents to verify information against multiple sources and identify potential biases or inconsistencies. This helps to mitigate the risk of hallucination and provide users with more trustworthy information. Iterative feedback loops. The system incorporates feedback loops, allowing users to refine their queries and the system to learn from its mistakes. This iterative process improves the accuracy and relevance of the responses over time. Benefits of using Agentic RAG. Improved accuracy. By employing multiple retrieval strategies and verification mechanisms, Agentic RAG delivers more accurate and reliable responses. Enhanced relevance. Adaptive retrieval strategies ensure that only the most relevant documents are retrieved, leading to more focused and informative responses. Reduced hallucinations. Verification agents minimize the risk of generating inaccurate or fabricated information. Increased efficiency. Pre-processing and chunking techniques optimize the retrieval process, leading to faster response times. Better handling of complex queries. Query decomposition and multi-hop reasoning enable the system to answer complex questions that traditional RAG systems struggle with. In conclusion, Agentic RAG provides a powerful and flexible framework for navigating complex document collections, enabling organizations to unlock valuable insights and drive better decision-making. Mastering iterative query refinement in Agentic AI. In the realm of Agentic AI, the ability to effectively refine queries iteratively is paramount to achieving desired outcomes. Our approach focuses on empowering agents with the capability to learn from feedback, adapt their strategies, and progressively improve their understanding of complex tasks. Why iterative query refinement matters. Enhanced accuracy. Refining queries based on initial results allows agents to narrow their focus and eliminate ambiguity, leading to more accurate and relevant responses. Improved efficiency. By learning from each iteration, agents minimize wasted resources and converge on the optimal solution faster. Complex problem solving. Many real-world problems require a step-by-step approach. Iterative refinement enables agents to break down complex tasks into manageable subqueries. Adaptability. Agents can adapt to changing environments and evolving information by continually refining their queries based on new data. Our methodology. We employ a multifaceted approach to iterative query refinement, incorporating feedback loops. Agents receive feedback on the relevance and accuracy of their responses, allowing them to adjust their queries accordingly. This feedback can be human-provided, system-generated, or derived from evaluation metrics. Contextual awareness. Agents maintain a memory of previous interactions and use this context to inform subsequent queries, ensuring consistency and coherence. Knowledge graph integration. Leverage knowledge graphs to enhance understanding of relationships and dependencies, enabling more informed query refinement. Natural language understanding. NLU. Advanced NLU techniques allow agents to interpret the nuances of user feedback and adapt their query strategies effectively. Reinforcement learning. We utilize reinforcement learning techniques to train agents to optimize their query refinement strategies over time. Benefits of our approach. Higher quality outputs, achieve more accurate, relevant, and insightful results. Reduce development costs, streamline the development process by enabling agents to learn and adapt autonomously. Increased scalability, handle complex tasks and large datasets with greater efficiency. Improved user experience, deliver more intuitive and responsive interactions. Explore further. Interested in learning more about our iterative query refinement techniques and how they can benefit your agentic AI applications? Contact us today to discuss your specific needs and explore potential solutions. You can also download our white paper on the topic. Beyond semantic search, the logic layer of Agentic RAG. While semantic search excels at finding relevant information based on meaning, Agentic Retrieval-Augmented Generation, RAG, demands a higher level of reasoning. This section explores how we move beyond simply finding similar passages to implementing a logic layer that enables our agents to understand contextual nuance, going beyond keyword matching to grasp the intent behind user queries and the complexities within retrieved documents. Reason about relationships, identifying connections between disparate pieces of information, inferring missing data, and drawing logical conclusions. Prioritize and synthesize information, evaluating the credibility and relevance of retrieved sources to construct coherent and insightful answers. Execute complex reasoning tasks, supporting multi-hop reasoning, constraint satisfaction, and other sophisticated cognitive processes necessary for advanced problem solving. Our approach to building this logic layer involves knowledge graph integration, leveraging knowledge graphs to represent entities, relationships, and concepts explicitly, enabling structured reasoning and inference. Rule-based systems, implementing rules and constraints that guide the reasoning process and ensure accuracy and consistency. Inference engines, utilizing inference engines to automatically deduce new information based on existing knowledge and retrieved context. Prompt engineering for logical reasoning, crafting prompts that encourage large language models, LLMs, to engage in logical deduction, abductive reasoning, and other higher-order cognitive functions. By incorporating a robust logic layer into our Agentic RAG framework, we empower our agents to provide more accurate, insightful, and contextually relevant responses, transforming simple information retrieval into a powerful problem-solving tool. Examples of the logic layer in action may include filtering information based on a user's profile and preferences, rejecting claims without supporting data, or answering questions based on contradictory or incomplete information. See the case studies below to explore real-world applications and the impact of our logic layer on performance and user experience. The future of enterprise knowledge bases, Agentic RAG explained. Enterprise knowledge bases are evolving beyond simple document repositories. They're becoming intelligent, proactive systems capable of understanding complex queries and delivering highly relevant, contextualized information. At the forefront of this evolution is Agentic Retrieval-Augmented Generation, Agentic RAG. This section delves into Agentic RAG, its transformative potential for enterprises, and how it's shaping the future of knowledge management. What is Agentic RAG? Traditional RAG systems combine information retrieval with language generation. They retrieve relevant documents from a knowledge base based on a user's query and then use a large language model, LLM, to generate an answer grounded in those documents. Agentic RAG takes this a step further by introducing an agentic component. This means the system doesn't just passively retrieve and generate, it actively plans, reasons, and executes steps to find the best possible answer. Key characteristics of Agentic RAG include iterative refinement. Agents can refine their search queries based on initial results, iteratively narrowing down the scope and improving the quality of retrieved information. Multi-hop reasoning. They can perform multi-step reasoning, combining information from multiple sources to answer complex questions that require synthesis and inference. Tool usage. Agents can leverage external tools, example databases, APIs, search engines, to augment their knowledge base and gather additional relevant information. Personalization and contextualization. Agents can tailor responses to the user's role, department, and past interactions, providing highly personalized and contextualized answers. Fact verification and source attribution. Emphasis is placed on verifying information from multiple sources and clearly attributing the origin of facts used in generated responses. Benefits of Agentic RAG for enterprises. Implementing Agentic RAG offers significant advantages for organizations seeking to improve knowledge accessibility and utilization. Enhanced accuracy and relevance. Iterative refinement and tool usage lead to more accurate and relevant answers compared to traditional RAG. Improved efficiency. Automated reasoning and planning streamline the information retrieval process, saving time and resources. Deeper insights. Multi-hop reasoning unlocks deeper insights by connecting disparate pieces of information and enabling complex problem solving. Increased user satisfaction. Personalized and contextualized responses improve user experience and encourage knowledge base adoption. Better decision making. Access to accurate, relevant, and comprehensive information empowers employees to make better informed decisions. Key considerations for implementation. Successfully implementing Agentic RAG requires careful planning and consideration of the following factors. Knowledge base quality. The accuracy and completeness of the underlying knowledge base are crucial for Agentic RAG performance. Regular maintenance and updates are essential. Agent design. Designing effective agents that can reason, plan, and execute tasks efficiently is a critical aspect of Agentic RAG development. Tool integration. Seamless integration with relevant tools and APIs is necessary to augment the agent's knowledge and capabilities. Security and privacy. Implementing robust security measures to protect sensitive information and ensure data privacy is paramount. Evaluation and monitoring. Continuously evaluating the performance of Agentic RAG systems and monitoring user feedback is essential for ongoing optimization. Conclusion. Agentic RAG represents a significant advancement in enterprise knowledge management. By leveraging the power of agents, organizations can unlock the full potential of their knowledge bases, empowering employees with the right information at the right time to drive innovation and improve business outcomes. Embracing Agentic RAG is not just about improving search, it's about building a truly intelligent and responsive knowledge ecosystem. Agentic RAG versus Standard RAG, key differences and use cases. Standard RAG, Retrieval-Augmented Generation. Standard RAG, Retrieval-Augmented Generation, is a straightforward approach that enhances large language models, LLMs, with external knowledge. It operates in 3 primary steps. Retrieval. Given a user query, relevant documents are retrieved from a knowledge base, example a vector database. Augmentation, the retrieved documents are combined with the original user query to form an enriched context. Generation, the LLM uses this enriched context to generate a response. Key characteristics. Simple and efficient for many applications. Relies on a single retrieval and generation cycle. Limited ability to handle complex queries requiring multiple reasoning steps. Effective for answering factual questions and providing information based on available documents. Use cases. Chatbots providing answers based on a knowledge base of FAQs. Question answering systems extracting information from documentation. Summarization of documents with external context. Agentic RAG, intelligent and adaptive retrieval. Agentic RAG builds upon standard RAG by introducing autonomous agents that can strategically plan and execute multiple retrieval and generation steps. It empowers the system to reason through complex tasks and adapt its approach based on intermediate results. Key characteristics. More sophisticated and flexible than standard RAG. Uses a planning agent to break down complex queries into smaller, manageable subtasks. Performs iterative retrieval and generation, refining the context based on each step. Capable of handling multi-hop reasoning and complex scenarios. Employs tools and APIs to interact with external environments. How it works. The Agentic RAG system utilizes an agent that leverages a planner to decide on a sequence of actions, example retrieve documents, generate text, execute code. Each action provides new insights that the agent uses to adjust the subsequent steps until a satisfactory solution is reached. This iterative process enables the system to address more intricate user requests. Use cases. Complex problem solving requiring multiple steps of reasoning. Interactive data analysis and exploration. Research tasks involving gathering and synthesizing information from multiple sources. Automated report generation based on diverse data sources. Comparative table. Feature standard RAG Agentic RAG. Complexity simple complex. Retrieval cycle single multiple, iterative. Reasoning ability limited advanced, multi-hop. Planning no planning planning agent. Adaptability limited highly adaptive. Use cases simple QA, summarization complex problem solving, data analysis. Choosing the right approach. The optimal choice between standard RAG and Agentic RAG depends on the complexity of the tasks and the desired level of autonomy. For straightforward queries and readily available information, standard RAG offers a simple and efficient solution. However, for tasks requiring complex reasoning, exploration, and interaction with external environments, Agentic RAG provides a more powerful and flexible approach. Improving data accuracy with self-correction in Agentic RAG. In today's data-driven landscape, accurate and reliable information is paramount. Retrieval-Augmented Generation, RAG, systems offer a powerful approach to leveraging external knowledge sources for enhanced language model performance. However, relying solely on retrieved data can introduce inaccuracies stemming from noisy or outdated information within the knowledge base. Our innovative solution addresses this challenge by incorporating a self-correction mechanism within an Agentic RAG framework. This approach moves beyond simple retrieval and generation, empowering the agent to critically evaluate and refine its outputs based on internal reasoning and external feedback. The core components of our strategy include iterative retrieval and evaluation. The agent doesn't just retrieve information once. Instead, it engages in multiple rounds of retrieval, evaluating the consistency and reliability of retrieved documents based on predefined criteria, example source credibility, corroboration with other sources. Reasoning-based correction, leveraging its internal reasoning capabilities, the agent identifies potential errors or inconsistencies in its initial response. This involves analyzing the retrieved data for logical flaws, contradictions, or gaps in information. External validation and refinement. When uncertainty persists, the agent can query specialized tools or APIs for fact-checking or supplementary information. This external validation process allows for evidence-based correction of inaccuracies. Knowledge graph integration. Optional integrating a knowledge graph can provide a structured representation of factual information, enabling the agent to cross-reference and validate its retrieved data against established relationships and entities. By incorporating self-correction into the RAG pipeline, we significantly improve data accuracy and reduce the risk of propagating misinformation. This leads to more reliable answers. Users can trust the information provided by the system, knowing that it has been rigorously validated and corrected. Reduced hallucinations. The agent is less likely to generate false or fabricated information. Improved confidence scores. The system can provide more accurate confidence scores for its responses, indicating the level of certainty associated with the information presented. Enhanced user experience. Users benefit from a more trustworthy and informative interaction. Our self-correcting Agentic RAG approach is particularly valuable in domains where data accuracy is critical, such as scientific research, financial analysis, and legal information retrieval. We offer customizable solutions tailored to your specific data sources and application requirements. Contact us today to learn how we can help you build a more accurate and reliable RAG system. How Agentic RAG handles contradictory information in large datasets. Agentic Retrieval-Augmented Generation, RAG, systems face a significant challenge when processing large datasets containing contradictory information. Unlike traditional RAG models, Agentic RAG employs a more sophisticated approach to navigate these inconsistencies and provide more accurate and contextually relevant answers. The challenge: inconsistent data and hallucinations. Large datasets often contain conflicting information due to various factors, including multiple sources. Data from different sources may offer conflicting viewpoints or outdated facts. Bias: datasets can reflect biases present in the data collection or annotation process. Errors: inaccuracies and errors can occur during data entry, processing, or aggregation. Evolution of knowledge: information can become outdated or superseded by new discoveries. When faced with contradictory information, standard RAG models can provide inaccurate answers, selecting and presenting the wrong or outdated information. Generate contradictory responses, presenting multiple conflicting statements without resolution. Hallucinate information, inventing facts or connections to resolve the contradiction, leading to unreliable outputs. Agentic RAG solution: a multifaceted approach. Agentic RAG addresses these challenges by incorporating agent-based reasoning and decision-making into the RAG pipeline. This enables the system to source evaluation and trust assessment. Agentic RAG evaluates the credibility and reliability of information sources. This might involve analyzing source metadata, assessing author reputation, or cross-referencing information with other trusted sources. A trust score can be assigned to each source. Conflict detection and resolution. The system identifies contradictory information within the retrieved context. It then employs various strategies to resolve the conflict, such as temporal reasoning, prioritizing information from more recent sources. Authority-based resolution, favoring information from sources with higher authority or expertise on the specific topic. Consensus-based resolution, identifying the most common or widely accepted information across multiple sources. Stating uncertainty. If a clear resolution is not possible, the system can acknowledge the contradiction and present multiple perspectives with appropriate caveats. Contextual understanding and reasoning. The agent analyzes the query and the retrieved context to understand the underlying intent and identify relevant biases. This allows the system to provide more nuanced and context-aware answers, acknowledging potential limitations or alternative perspectives. Knowledge integration and reasoning. Agentic RAG can leverage external knowledge graphs or pre-trained knowledge bases to validate information and identify potential inconsistencies. This allows the system to enrich its understanding and provide more accurate responses. Iterative refinement and learning. The system can learn from its past experiences and adapt its conflict resolution strategies over time. This can involve tracking the accuracy of its responses and adjusting its source evaluation criteria based on feedback. Benefits of Agentic RAG in handling contradictory information. Improved accuracy, provides more reliable and factual answers by resolving conflicts and mitigating the impact of inconsistent data. Enhanced context awareness, offers more nuanced and contextually relevant responses that acknowledge potential limitations and alternative perspectives. Reduced hallucinations, minimizes the generation of fabricated information by relying on verified sources and established knowledge. Increased trustworthiness, builds trust with users by providing transparent and reliable information. By integrating agent-based reasoning and sophisticated conflict resolution mechanisms, Agentic RAG offers a significant improvement over traditional RAG models in handling contradictory information within large datasets, ultimately leading to more accurate, reliable, and trustworthy AI-powered applications. Understanding the Agentic RAG architecture. Agentic Retrieval-Augmented Generation, RAG, systems represent a significant evolution in AI-powered knowledge retrieval and generation. Unlike traditional RAG, which primarily focuses on augmenting a language model's input with retrieved context, Agentic RAG introduces autonomous agents that orchestrate the retrieval, generation, and reasoning processes. This architecture empowers the system to dynamically adapt its strategy based on the specific query and available information, leading to more accurate, relevant, and insightful responses. Key components of an Agentic RAG system. The Agent Manager. This central control unit orchestrates the entire process. It analyzes the user query, breaks it down into subtasks if necessary, and assigns these tasks to specific agents. The Agent Manager monitors progress, handles dependencies between agents, and consolidates the final response. Retrieval agents. These agents are responsible for identifying and retrieving relevant information from various knowledge sources. They can employ different retrieval strategies, such as keyword search, semantic search, graph traversal, and vector database lookups. Agentic RAG allows for multiple retrieval agents, each specialized in a particular knowledge domain or retrieval technique. Reasoning agents. These agents perform logical reasoning and inference based on the retrieved information. They can use techniques like chain of thought reasoning, knowledge graph reasoning, or symbolic reasoning to derive insights and uncover hidden relationships within the data. Generation agents. These agents are responsible for generating the final response to the user query. They leverage the retrieved information and the insights derived by the reasoning agents to produce coherent, informative, and contextually relevant answers. Different generation agents can be used for different types of responses, such as summaries, explanations, or creative content. Knowledge sources. This encompasses the various databases, documents, APIs, and other information sources that the agents can access. Effective knowledge management and organization are crucial for the performance of the entire system. Observation and feedback loop. Agentic RAG systems often incorporate a feedback loop where the agents evaluate the quality of their actions and adjust their strategies accordingly. This self-improvement mechanism allows the system to learn from its mistakes and continuously improve its performance. Information flow and workflow. User query. The process begins with a user submitting a query to the system. Query analysis. The agent manager analyzes the query to understand the user's intent and determine the required tasks. Task assignment. The agent manager assigns tasks to specific agents based on their expertise and capabilities. Retrieval and reasoning. Retrieval agents retrieve relevant information, and reasoning agents perform logical inference. Information aggregation. The agent manager gathers the outputs from the retrieval and reasoning agents. Response generation. The generation agent crafts a final response based on the aggregated information. Response delivery. The generated response is presented to the user. Feedback and optimization. Optional. The system may collect user feedback or internal metrics to evaluate the quality of the response and optimize its performance. Benefits of Agentic RAG. Improved accuracy. By using multiple agents with specialized skills, Agentic RAG can retrieve more relevant information and reason more effectively, leading to more accurate answers. Enhanced relevance. The dynamic nature of Agentic RAG allows it to tailor its response to the specific query, ensuring that the information provided is highly relevant to the user's needs. Increased explainability. The modular architecture of Agentic RAG makes it easier to understand how the system arrived at its conclusions, improving transparency and trust. Scalability and adaptability. The agent-based approach allows for easy expansion of the system's capabilities by adding new agents or knowledge sources. This overview provides a foundation for understanding the architecture of an Agentic RAG system. In the following sections, we will delve deeper into each component and explore the various techniques and technologies used to implement these systems effectively. Optimizing latency in Agentic RAG pipelines. Agentic RAG, Retrieval-Augmented Generation, Pipelines offer powerful capabilities for complex question answering, reasoning, and knowledge integration. However, latency can be a significant bottleneck, especially in real-time applications. This section explores key strategies for optimizing latency in your Agentic RAG pipelines. Strategies for latency reduction. Chunk optimization and indexing. Fine-tune chunk size and overlap based on your specific knowledge base and query patterns. Experiment with different chunking strategies, example semantic chunking, to minimize the amount of irrelevant information retrieved. Choose the right indexing method, example vector databases like Chroma, Bayes, or Weaviate, based on your data scale, query patterns, and accuracy requirements. Evaluate index rebuild frequency and update strategies. Implement metadata filtering within the index to narrow down search results quickly and efficiently. Query optimization and reformulation. Refine the query formulation process to generate more effective and focused queries. Explore techniques like query expansion, query rewriting, and multi-hop query generation. Employ query understanding techniques to identify the key entities and relationships within the query, allowing for more precise retrieval. Implement query caching to avoid redundant retrievals for frequently asked questions. Agent orchestration and parallelization. Optimize the agent orchestration logic to minimize the number of sequential steps required to answer a query. Explore techniques like subquery decomposition and parallel agent execution. Identify independent tasks within the pipeline that can be parallelized to reduce overall execution time. Carefully manage the dependencies between agents to avoid unnecessary delays and ensure efficient resource utilization. Model optimization and acceleration. Choose the appropriate models for each stage of the pipeline based on their accuracy, latency, and resource requirements. Consider using smaller, more efficient models where possible. Employ model quantization and other optimization techniques to reduce model size and inference latency. Utilize hardware acceleration, example GPUs, TPUs, to speed up computationally intensive tasks like embedding generation and language model inference. Caching and memoization. Implement caching mechanisms at various stages of the pipeline to avoid redundant computations. Cache frequently retrieved documents, generated embeddings, and intermediate results. Use memoization techniques to store the results of expensive function calls and reuse them when the same inputs are encountered again. Infrastructure and deployment. Deploy the pipeline on infrastructure that provides sufficient resources, CPU, memory, GPU, to handle the expected workload. Optimize the deployment configuration to minimize network latency and ensure efficient resource utilization. Implement monitoring and alerting to identify and address performance bottlenecks. Tools and technologies. Several tools and technologies can aid in optimizing latency in Agentic RAG pipelines. These include vector databases, Chroma, Bayes, Weaviate, Pinecone. Model optimization libraries, TensorFlow Lite, ONNX Runtime, PyTorch Mobile. Caching libraries, Redis, MEMC8. Profiling tools, PySpy, cProfile. Orchestration frameworks, LangChain, Haystack, LlamaIndex. Conclusion. Optimizing latency in Agentic RAG pipelines is crucial for delivering a seamless and responsive user experience. By carefully considering the strategies outlined above and leveraging the appropriate tools and technologies, you can significantly reduce latency and unlock the full potential of your Agentic RAG applications. The power of planning, how agents strategize information retrieval. In the dynamic landscape of information access, successful agents don't just react, they plan. Effective information retrieval hinges on strategic foresight and the ability to anticipate the most efficient path to relevant knowledge. This section explores the crucial role of planning in agent-driven information retrieval systems. Strategic goal definition. Before embarking on any information search, agents must first define clear and measurable goals. This involves goal articulation, precisely defining the information needed to satisfy a user's request or solve a problem. Relevance assessment, establishing criteria for determining the relevance of retrieved information. Scope limitation, defining the boundaries of the search to avoid information overload. Search strategy formulation. Once goals are defined, agents formulate search strategies, which encompass keyword selection, identifying the most effective keywords and phrases for querying information sources. Source selection, choosing the most appropriate databases, search engines, or knowledge repositories to consult. Query refinement, iteratively adjusting search queries based on initial results. Constraint management, factoring in limitations such as time constraints, access restrictions, and budget limitations. Planning algorithms and techniques. Agents leverage various planning algorithms to optimize their information retrieval strategies. Heuristic search, employing heuristics to guide the search process and prioritize promising paths. Reinforcement learning, learning optimal search strategies through trial and error, adapting to different information environments. Knowledge representation, utilizing knowledge graphs and ontologies to represent relationships between concepts and facilitate semantic search. Multi-agent coordination, coordinating multiple agents to collaboratively search and synthesize information from diverse sources. Benefits of strategic planning. Planning in information retrieval offers significant advantages. Improved efficiency, reduced search time and resource consumption. Enhanced accuracy, higher precision and recall of relevant information. Adaptive learning, ability to learn and adapt to evolving information landscapes. Proactive discovery, identifying potential information gaps and proactively seeking out relevant knowledge. By embracing the power of planning, agents can transform the information retrieval process, delivering more accurate, efficient, and insightful results. Agentic RAG for legal tech, automating complex case research. In the fast-paced and detail-oriented world of legal technology, efficient and accurate case research is paramount. Manually sifting through vast legal databases and case files consumes valuable time and resources, hindering lawyers and legal professionals from focusing on strategic analysis and client advocacy. Our Agentic Retrieval-Augmented Generation (RAG) system revolutionizes legal case research by automating the discovery, synthesis, and application of relevant information, significantly improving productivity and outcomes. What is Agentic RAG? Traditional RAG systems enhance large language models, LLMs, by providing them with external knowledge retrieved from a vector database. Our Agentic RAG takes this a step further by introducing autonomous agents that intelligently explore and interact with legal databases, court records, and legal knowledge repositories. These agents leverage a combination of advanced techniques, including intelligent retrieval, utilizing semantic search and advanced filtering techniques to identify the most relevant legal documents based on complex queries. Autonomous exploration, employing multi-hop reasoning and guided exploration to uncover hidden connections and relevant precedents across multiple sources. Dynamic synthesis, summarizing and synthesizing information from multiple documents to provide concise and comprehensive overviews of legal issues. Adaptive learning, continuously learning from user feedback and search history to refine retrieval strategies and improve accuracy over time. Contextual understanding, understanding the nuanced legal context of a query to ensure the retrieved information is relevant and applicable to the specific case. Key benefits for legal professionals. Significant time savings, automate tedious and time-consuming legal research tasks, freeing up lawyers to focus on higher-value activities. Improved accuracy, reduce the risk of missing crucial information by leveraging AI-powered search and analysis. Enhanced case strategy, gain deeper insights into legal precedents and arguments to develop stronger and more effective case strategies. Increased productivity, handle a larger caseload with greater efficiency and accuracy. Cost reduction, minimize the costs associated with manual legal research and discovery. How our Agentic RAG works. Query input, users input a legal question or describe the specifics of a case. Agent orchestration, our system orchestrates multiple intelligent agents, each specializing in a specific task, example document retrieval, precedent analysis, legal definition lookup. Knowledge retrieval, agents autonomously explore legal databases and knowledge repositories to identify relevant documents and information. Information synthesis, the system synthesizes information from multiple sources, creating a comprehensive and concise overview of the legal issues. Response generation, the system generates a clear and concise answer to the user's query, supported by evidence from the retrieved documents. Feedback loop, users provide feedback on the accuracy and relevance of the results, allowing the system to continuously improve its performance. Ready to transform your legal research? Contact us today to learn more about how our Agentic RAG system can help you automate complex case research and unlock significant benefits for your legal practice. Schedule a demo and experience the future of legal tech. Implementing Agentic RAG with LangGraph and Llama Index. This section details the practical implementation of Agentic RAG, Retrieval-Augmented Generation, using the powerful combination of LangGraph and Llama Index. Agentic RAG elevates traditional RAG by incorporating autonomous agent behaviors, enabling more dynamic and context-aware information retrieval and generation. Key components and architecture. Llama Index provides the core data ingestion, indexing, and retrieval capabilities. We leverage Llama Index for efficient knowledge base management and semantic search. LangGraph serves as the orchestration framework, defining the agentic workflow. LangGraph allows us to model the decision-making process as a graph, enabling iterative retrieval, reasoning, and refinement. Agents, individual agents within the LangGraph network perform specific tasks, such as initial query generation, document retrieval, summarization, and final answer synthesis. Each agent is typically powered by a large language model, LLM. Knowledge base, the index data repository managed by Llama Index. This can consist of documents, web pages, databases, or any other structured or unstructured data source. Implementation steps. Data ingestion and indexing, Llama Index. Load your data sources into Llama Index. Create an index, example vector store index, to enable efficient semantic search. Configure the index with appropriate embeddings and chunking strategies. Agent definition, LangGraph. Define the roles and responsibilities of each agent in the LangGraph workflow, example retriever agent, summarizer agent, answer synthesis agent. Implement each agent using a function or class, typically interacting with Llama Index or other external tools. Configure each agent's LLM and prompt templates. Graph construction, LangGraph. Define the nodes of the LangGraph, representing the agents. Define the edges of the LangGraph, representing the flow of information between agents. Implement conditional edges to enable dynamic routing based on agent outputs. Workflow execution, LangGraph. Initialize the LangGraph with an initial query. Execute the graph, allowing agents to iteratively retrieve, process, and refine information. Monitor the workflow execution and debug any issues. Output generation. The final agent in the graph synthesizes the information gathered by previous agents to generate the final answer. Post-process the output as needed for clarity and coherence. Example workflow. A typical Agentic RAG workflow might involve the following steps. Query generation agent formulates an initial query based on the user input. Retrieval agent uses Llama Index to retrieve relevant documents based on the query. Summarization agent summarizes the retrieved documents to extract key information. Answer synthesis agent combines the summaries to generate a comprehensive and accurate answer. Benefits of Agentic RAG. Improved accuracy, iterative retrieval and refinement lead to more accurate answers. Enhanced context awareness, agents can adapt to the context and retrieve relevant information from multiple sources. Increased efficiency, automated workflow reduces the need for manual intervention. Greater flexibility, the graph-based architecture allows for easy customization and extension. Code snippets, illustrative. Hashtag example, retriever agent using Llama Index. From llama_index.core import vector store index, simple directory reader. Hashtag load documents. Documents equals simple directory reader, data.load_data. Hashtag create index. Index equals vector store index.from_documents, documents. Query_engine equals index.as_query_engine. Def retrieval_agent, query. Results equals query_engine.query, query. Return results.response. Hashtag example, LangGraph implementation, simplified. From langgraph.graph import state graph. Hashtag define a state class, simplified. Class agent state. Query, str equals. Response, str equals. Hashtag define a simple agent. Def agent, state, agent state. Hashtag placeholder logic to return a response based on the query. Return response, f responding to query, state.query. Hashtag build graph. Workflow equals state graph, agent state. Workflow.add_node, agent, agent. Workflow.set_entry_point, agent. Graph equals workflow.compile. Hashtag example usage. For output in graph.stream, query, what is the capital of France? Sad face. For key, value in output.items. Print, f node key colon. Print, value. Further exploration. For deeper understanding and practical implementation, consider exploring the following resources. LlamaIndex documentation, https://docs.llamaindex.ai. LangGraph documentation, insert LangGraph documentation link here when available. Example notebooks and tutorials, search for Agentic RAG examples using LangGraph and LlamaIndex on platforms like GitHub and Colab. Why Agentic RAG is the next frontier for large language models. Large language models, LLMs, have demonstrated impressive capabilities in generating text, translating languages, and answering questions. However, their inherent limitations, such as knowledge cutoffs, hallucinations, and difficulty in adapting to dynamic information landscapes, hinder their applicability in real-world scenarios. Retrieval-Augmented Generation, RAG, significantly improves LLMs by grounding their responses in external knowledge sources, mitigating these limitations. While traditional RAG pipelines enhance LLMs with relevant information, they often lack the proactive and adaptive behavior required for complex tasks. They passively retrieve and inject information without actively planning, verifying, or refining the retrieved content. This is where Agentic RAG emerges as the next evolution. The power of Agentic RAG. Agentic RAG combines the strengths of RAG with the proactive decision-making capabilities of autonomous agents. This empowers LLMs with dynamic retrieval strategies. Instead of relying on fixed retrieval methods, agents can strategically choose the most appropriate retrieval tools and techniques based on the specific query and context. This could involve iteratively refining search queries, exploring multiple data sources, and prioritizing information based on relevance and reliability. Reasoning and planning, agents can break down complex queries into smaller, manageable subtasks, plan the necessary retrieval steps for each subtask, and reason about the retrieved information to synthesize comprehensive and accurate responses. Verification and validation, agents can actively verify the accuracy and trustworthiness of the retrieved information by cross-referencing sources, identifying potential biases, and mitigating the risk of hallucinations. Contextual adaptation, agents can continuously learn and adapt their retrieval strategies based on past interactions and user feedback, leading to improved performance over time. They can personalize the retrieval process to individual user needs and preferences. Task orchestration, Agentic RAG enables LLMs to perform complex tasks that require interacting with multiple tools and systems, such as making API calls, querying databases, and executing code. Benefits of embracing Agentic RAG. Adopting Agentic RAG offers several significant advantages. Enhanced accuracy and reliability, reduced hallucinations and increased factual correctness through active verification and validation. Improved contextual understanding, deeper analysis of user queries and dynamic adaptation to evolving information landscapes. Greater efficiency, streamlined retrieval processes and optimized resource utilization. Increased scalability, handling of complex and nuanced queries with greater ease. More human-like interactions, more natural and engaging conversations with LLMs. Conclusion. Agentic RAG represents a significant leap forward in the evolution of large language models. By integrating proactive decision-making and dynamic retrieval strategies, Agentic RAG unlocks new possibilities for LLMs, enabling them to tackle complex tasks with greater accuracy, reliability, and efficiency. As the field continues to evolve, Agentic RAG is poised to become an essential component of the next generation of AI-powered applications. Automating metadata filtering through agentic decision-making. In today's data-rich environment, effective metadata filtering is crucial for information discovery, efficient resource allocation, and regulatory compliance. However, traditional metadata filtering methods often rely on rigid, predefined rules, struggling to adapt to evolving data landscapes and complex query requirements. This section explores our innovative approach to automating metadata filtering through agentic decision-making, ADM. What is agentic decision-making for metadata filtering? Our ADM system leverages a network of intelligent agents, each specialized in a specific aspect of metadata analysis and filtering. These agents operate autonomously, communicating and collaborating to make informed decisions on which metadata entries should be included or excluded based on user queries, defined objectives, and learned patterns. Key features include adaptive filtering. Unlike static rules, the agents continuously learn from new data and user feedback, dynamically adjusting their filtering strategies to optimize performance and accuracy. Contextual understanding. The agents consider the broader context of the data and the user's intent, going beyond simple keyword matching to identify relevant metadata. Explainable decisions. The system provides insights into why specific filtering decisions were made, enhancing transparency and trust. Users can understand the reasoning behind the results and provide valuable feedback. Scalable architecture. The agent-based architecture allows for easy scalability, enabling efficient filtering of vast datasets with minimal performance degradation. Benefits of agentic metadata filtering. Implementing ADM for metadata filtering offers numerous advantages. Improved accuracy, reduced false positives and false negatives leading to more precise and reliable results. Increased efficiency. Automated filtering reduces manual effort and speeds up the information discovery process. Enhanced flexibility, adaptability to changing data landscapes and evolving user needs. Cost savings, reduced operational costs through automation and improved resource allocation. Better compliance, enhanced ability to meet regulatory requirements by ensuring data accuracy and accessibility. Use cases. Our ADM system is applicable across various industries and use cases, including data governance, automating data quality checks and ensuring metadata consistency. E-commerce, enhancing product search and recommendations based on accurate and relevant metadata. Healthcare, improving clinical data analysis and patient record management. Financial services, streamlining risk management and regulatory reporting. Learn more. Ready to see how agentic decision-making can transform your metadata filtering process? Contact us for a demo or to discuss your specific needs. You can also explore our case studies to see real-world examples of ADM in action. How to reduce token costs in Agentic RAG workflows. Agentic RAG workflows, while powerful, can quickly become expensive due to the iterative nature of prompting and reliance on large language models, LLMs. Optimizing token usage is crucial for maintaining cost-effectiveness without sacrificing performance. Here's a breakdown of key strategies. 1. Optimize prompting techniques. Prompt compression, reduce verbosity and use concise language. Avoid unnecessary explanations or instructions. Consider techniques like prompt engineering frameworks, example COT prompting with concise summaries, to maintain context with fewer tokens. One-shot/few-shot learning, provide a limited number of relevant examples to guide the LLM instead of lengthy detailed instructions. This can often achieve similar or better results with fewer tokens. Prompt caching, cache the results of common or repetitive prompts. If the same prompt is used multiple times, reuse the cached response to avoid recomputation. Implement proper cache invalidation strategies to maintain data integrity. Output formatting, specify a structured output format, example JSON, CSV, in your prompts. This reduces the LLM's freedom to generate verbose and potentially irrelevant text. 2. RAG optimization. Chunking strategy, experiment with different chunking methods, example fixed size, semantic chunking, sliding window, to find the optimal balance between context and token count. Smaller, more focused chunks can reduce the amount of information processed by the LLM. Vector database optimization. Index size, regularly review and optimize your vector index. Remove irrelevant or outdated documents to reduce the search space and improve retrieval efficiency. Similarity search parameters, fine-tune similarity search parameters, example top_k, distance metric, to retrieve only the most relevant documents. Avoid retrieving an excessive number of documents, which can increase token usage. Document filtering and ranking, implement pre-filtering and ranking mechanisms to prioritize the most relevant documents for the LLM. This ensures that the LLM only processes the most important information. Consider using metadata filtering or pre-ranking models to narrow down the document set. 3. Model selection and orchestration. Model tiering, use smaller, faster, and cheaper models for simpler tasks, example initial document filtering, summarizing retrieved context, and reserve more powerful models for complex reasoning and generation tasks. Early exit strategies, implement mechanisms to terminate the agentic workflow early if a satisfactory answer is found or if the workflow is deemed unlikely to succeed. This prevents unnecessary iterations and token consumption. Agent routing and specialization, design your agent architecture with specialized agents for different tasks. This allows you to use smaller, more focused models for each task, rather than relying on a single large model for everything. 4. Monitoring and evaluation. Token usage tracking, implement robust monitoring to track token usage for each step of the workflow. This allows you to identify areas where optimization is most needed. A/B testing, conduct A/B tests to compare the performance and cost effectiveness of different optimization strategies. Use metrics like accuracy, latency, and token usage to evaluate the results. Cost-aware design, design your workflows with token costs in mind from the outset. Prioritize cost-effective solutions and regularly review your design to identify potential areas for improvement. By implementing these strategies, you can significantly reduce token costs in your agentic RAG workflows while maintaining or even improving performance. Continuous monitoring and experimentation are essential to ensure that you are using the most efficient and cost-effective approach. Agentic RAG for healthcare, navigating sensitive medical records. The healthcare industry is brimming with vast amounts of unstructured data, including patient records, research papers, clinical trial results, and more. Extracting meaningful insights from this data is crucial for improving patient outcomes, accelerating research, and streamlining operations. However, accessing and utilizing this information comes with significant challenges, particularly concerning patient privacy and data security. Agentic Retrieval-Augmented Generation, RAG, offers a promising solution. This advanced AI approach combines the power of large language models, LLMs, with a retrieval mechanism that allows the model to access and incorporate relevant information from external knowledge sources before generating a response. In the context of healthcare, this means that an LLM can leverage a curated database of medical records, research articles, and clinical guidelines to provide accurate and contextually relevant answers to complex medical queries. Key advantages of Agentic RAG in healthcare. Improved accuracy and reliability. By grounding responses in verified medical data, Agentic RAG minimizes the risk of hallucinations and inaccurate information, crucial in a field where precision is paramount. Enhanced privacy and security. Agentic RAG can be implemented with strict access control measures, ensuring that only authorized personnel can access sensitive medical records. Furthermore, techniques like differential privacy can be integrated to further protect patient anonymity. Faster and more efficient information retrieval. Quickly access relevant patient information, diagnostic codes, and treatment options, saving valuable time for healthcare professionals. Personalized patient care. Generate tailored treatment plans and educational materials based on a patient's specific medical history and current condition. Accelerated research and drug discovery. Analyze large data sets of medical records and research papers to identify trends, uncover new drug targets, and improve clinical trial design. Reduce burden on healthcare professionals. Automate routine tasks such as answering frequently asked questions, summarizing patient records, and generating reports. Addressing key challenges. Implementing Agentic RAG in healthcare requires careful consideration of several key challenges. Data quality and standardization, ensuring data accuracy, completeness, and consistency is crucial for reliable results. Data cleaning and standardization are essential steps. Regulatory compliance, HIPAA, GDPR adhering to strict data privacy regulations is paramount. Implementing robust security measures and obtaining necessary consents are critical. Model explainability and trust, healthcare professionals need to understand how the model arrived at its conclusions to trust its recommendations. Explainable AI, XAI, techniques are vital. Bias mitigation, identifying and mitigating potential biases in the data and model is essential to ensure fairness and equity in healthcare outcomes. Ethical considerations, carefully consider the ethical implications of using AI in healthcare, including issues of autonomy, responsibility, and accountability. Our team is dedicated to developing and deploying Agentic RAG solutions that address these challenges and unlock the transformative potential of AI in healthcare. We offer expertise in data preparation and pre-processing, model development and training, security and compliance, explainable AI, ethical AI. Contact us to learn more about how Agentic RAG can revolutionize your healthcare organization. The ethics of autonomous retrieval, ensuring bias-free AI. As autonomous retrieval systems become increasingly prevalent in various sectors, from legal discovery to medical diagnosis, the ethical implications of their use demand careful consideration. At the heart of this ethical landscape lies the imperative to mitigate bias and ensure fairness in AI-driven search and information retrieval. Understanding bias in autonomous retrieval. Bias can infiltrate autonomous retrieval systems at multiple stages, leading to skewed results and potentially discriminatory outcomes. Common sources of bias include training data bias. If the data used to train the retrieval system reflects existing societal biases, the AI will likely perpetuate and amplify those biases in its search results. This includes biases related to gender, race, ethnicity, socioeconomic status, and other sensitive attributes. Algorithmic bias. Even with unbiased data, the algorithms themselves can inadvertently introduce bias through their design, implementation, or optimization criteria. This can stem from subtle choices in feature selection, ranking algorithms, or relevance weighting. User interaction bias. User queries and interaction patterns can reinforce existing biases. For example, if users disproportionately search for information about a particular group, the system may incorrectly infer that this group is more relevant to certain topics. Presentation bias. The way search results are presented can influence user perception and decision-making. Presenting certain results more prominently than others, even if algorithmically justified, can create unfair advantages or disadvantages. Our commitment to ethical AI. We are committed to developing and deploying autonomous retrieval systems that are fair, transparent, and accountable. Our approach to mitigating bias encompasses the following key strategies. Data auditing and pre-processing. We rigorously audit our training data for potential biases and implement pre-processing techniques to mitigate their impact. This includes techniques like data augmentation, reweighting, and adversarial debiasing. Algorithmic fairness techniques. We employ a variety of algorithmic fairness techniques to minimize bias in our retrieval algorithms. This includes developing bias-aware ranking algorithms, using counterfactual fairness methods, and ensuring demographic parity in search results. Transparency and explainability. We strive to make our systems as transparent and explainable as possible. This allows users to understand how the system works, identify potential biases, and hold us accountable for our actions. Continuous monitoring and evaluation. We continuously monitor and evaluate our systems for bias and fairness. We use a variety of metrics to assess the impact of our systems on different groups and identify areas for improvement. Human oversight and feedback. We believe that human oversight is essential for ensuring the ethical use of autonomous retrieval systems. We incorporate human feedback into our development process and provide mechanisms for users to report potential biases. Join the conversation. We believe that addressing the ethical challenges of autonomous retrieval requires a collaborative effort. We encourage researchers, developers, policymakers, and the public to engage in open discussions about these issues. Contact us to learn more about our commitment to ethical AI and how you can contribute to this important conversation. Developing custom agents for domain-specific RAG applications. Unlock the true potential of Retrieval-Augmented Generation, RAG, by developing custom agents tailored to your specific domain. Standard RAG pipelines often fall short when dealing with complex, nuanced information or requiring sophisticated reasoning within a specialized field. Building custom agents allows you to fine-tune the process, resulting in more accurate, relevant, and insightful responses. Key advantages of custom agent development. Enhance domain expertise. Integrate domain-specific knowledge bases, ontologies, and reasoning rules directly into the agent's workflow. Improved accuracy and relevance. Reduce hallucination and improve the quality of generated content by focusing the search and generation process on pertinent information. Complex reasoning capabilities. Enable agents to perform sophisticated reasoning tasks, such as inferencing, deduction, and problem-solving, relevant to your domain. Personalized user experiences. Tailor the agent's interaction style and response format to meet the specific needs of your users. Optimized performance. Fine-tune the agent's architecture and parameters to achieve optimal performance for your specific use case. Increased control and transparency. Gain full control over the agent's behavior and understand the reasoning behind its responses. Our expertise. We specialize in the development of custom agents for RAG applications across a variety of domains, including financial services, regulatory compliance, investment analysis, fraud detection, healthcare, clinical decision support, drug discovery, patient education, legal, contract review, legal research, risk assessment, manufacturing, process optimization, predictive maintenance, quality control, education, personalized learning, tutoring, content creation. Our development process. Requirements gathering, in-depth analysis of your specific domain, data sources, and user needs. Agent design, architecture design, including knowledge base integration, reasoning engine selection, and response generation strategies. Development and implementation, coding, testing, and deployment of the custom agent. Evaluation and refinement, rigorous testing and performance evaluation, followed by iterative refinement based on user feedback. Maintenance and support, ongoing maintenance, updates, and support to ensure the agent's continued performance and reliability. Ready to unlock the power of custom agents for your domain-specific RAG application? Contact us today to discuss your project. Routing queries, how Agentic RAG selects the best data source. In complex information retrieval scenarios, simply throwing a query at a single data source often yields suboptimal results. Agentic Retrieval-Augmented Generation, RAG, takes a more intelligent approach by employing a routing mechanism to determine the most relevant data source for each specific query. The power of intelligent routing. Instead of blindly retrieving from a single source, Agentic RAG leverages an agent a sophisticated decision-making module to analyze the incoming query and intelligently route it to the most appropriate knowledge base. This agent considers factors such as query semantics, understanding the underlying meaning and intent of the query. Data source content, knowledge of the information contained within each available data source, example product manuals, FAQ databases, research papers. Metadata and tags, utilizing metadata associated with each data source to guide routing decisions. Prior performance, learning from past routing decisions and their corresponding results to improve accuracy over time. Benefits of routing in Agentic RAG. Improved accuracy, by focusing the search on the most relevant data source, the system avoids irrelevant or noisy information, leading to more accurate answers. Reduced latency, limiting the search to a subset of data sources reduces the overall retrieval time, improving the speed of response. Enhanced scalability, as the number of data sources grows, the routing mechanism ensures efficient utilization of resources by preventing the system from searching through all sources for every query. Increased contextual relevance, routing allows for the selection of data sources that are specifically tailored to the context of the query, leading to more informative and relevant responses. Routing strategies and techniques. Several techniques can be employed to implement the routing agent in Agentic RAG. Keyword-based routing, a simple approach that relies on matching keywords in the query to predefined keywords associated with each data source. Semantic similarity routing, utilizing techniques like sentence embeddings to measure the semantic similarity between the query and the content of each data source. Machine learning-based routing, training a machine learning model to predict the most relevant data source based on a variety of features extracted from the query and data source metadata. Hybrid approaches, combining multiple routing techniques to leverage their individual strengths and achieve optimal performance. Conclusion. Routing is a crucial component of Agentic RAG, enabling intelligent and efficient information retrieval. By strategically selecting the best data source for each query, Agentic RAG delivers more accurate, relevant, and timely responses, ultimately enhancing the user experience. Building multi-agent RAG systems for collaborative problem solving. Harness the power of multiple agents working in concert to tackle complex problems with our multi-agent retrieval-augmented generation, RAG, systems. This advanced approach moves beyond single-agent RAG, enabling collaborative problem solving by distributing tasks, leveraging diverse knowledge sources, and aggregating expertise. Key benefits. Enhanced accuracy, agents can cross-validate information and identify biases, leading to more reliable and accurate results. Improved contextual understanding, by pooling knowledge from various domains, the system gains a deeper understanding of the problem context. Increased problem-solving capabilities, decompose complex problems into smaller, more manageable tasks that are distributed among specialized agents. Scalability and efficiency, agents can work in parallel, accelerating the problem-solving process and handling large volumes of information. Reduced hallucinations, collaborative validation and access to diverse knowledge bases minimize the risk of generating inaccurate or fabricated information. Our approach. We specialize in designing and implementing multi-agent RAG systems tailored to your specific needs. Our methodology includes agent definition and specialization, defining the roles, responsibilities, and expertise of each agent within the system. Knowledge graph integration, connecting agents to relevant knowledge sources, including internal databases, external APIs, and public datasets. Communication and coordination mechanisms, implementing protocols for agents to communicate, share information, and coordinate their efforts. RAG pipeline optimization, fine-tuning the retrieval and generation processes for each agent to maximize performance. Evaluation and monitoring, establishing metrics to track the system's performance and identify areas for improvement. Use cases. Multi-agent RAG systems are ideal for a wide range of applications, including customer service automation, resolve complex customer inquiries by routing them to specialized agents with expertise in different product areas. Scientific research, accelerate scientific discovery by enabling agents to collaboratively analyze research papers, synthesize findings, and generate new hypotheses. Financial analysis, improve investment decisions by leveraging agents to analyze market trends, assess risk factors, and generate investment recommendations. Code generation, develop complex software applications by distributing coding tasks among specialized agents. Content creation, generate high-quality content by enabling agents to collaboratively research, write, and edit articles, blog posts, and other materials. Let's discuss your project. Ready to explore the potential of multi-agent RAG systems for your organization? Contact us today for a consultation to discuss your specific needs and how we can help you build a collaborative problem-solving solution. The impact of long context windows on Agentic RAG strategy. Recent advancements in large language models, LLMs, have significantly increased context window sizes, fundamentally changing the landscape of retrieval-augmented generation, RAG, strategies, particularly within agentic workflows. This section explores how longer context windows impact the effectiveness and efficiency of Agentic RAG, highlighting key advantages and challenges. Enhanced agent capabilities and reasoning. Longer context windows empower agents to perform more complex reasoning tasks by providing access to a richer and more comprehensive understanding of the retrieved information. This allows agents to integrate multiple documents seamlessly. Agents can synthesize information from various sources without the need for iterative retrieval and processing, leading to more holistic and accurate responses. Maintain context across multiple steps. In multi-turn conversations or complex task execution, longer windows allow agents to retain crucial context from previous interactions, improving coherence and reducing information loss. Improve contextual understanding. By having access to broader background information, agents can better understand the nuances and subtleties within the retrieved content, leading to more insightful interpretations. Enable more sophisticated planning. Agents can use the extended context to plan more complex sequences of actions, consider downstream consequences, and adapt to changing circumstances. Improved retrieval and relevance. Longer context windows also influence the effectiveness of the retrieval stage itself. By considering more of the surrounding context within documents, retrieval systems can reduce noise and improve signal. The extended context allows for better disambiguation of ambiguous terms and improved identification of relevant information. Enhance semantic search. Retrieval models can leverage the broader context to understand the semantic meaning of queries more accurately, leading to more relevant search results. Enable fine-grained contextual filtering. Agents can filter retrieved documents based on specific contextual cues, ensuring that only the most relevant information is presented to the LLM. Challenges and considerations. While longer context windows offer significant advantages, several challenges and considerations must be addressed. Computational cost. Processing longer contexts requires more computational resources, increasing latency and cost. Careful optimization is crucial to ensure efficient performance. Attention dilution. LLMs may struggle to attend equally to all parts of a very long context window, potentially leading to information loss or misinterpretation. Strategies for focusing attention on the most relevant information are critical. Context management complexity. Managing and organizing large amounts of contextual information requires sophisticated techniques for chunking, summarizing, and prioritizing information. Evaluation metrics. Traditional evaluation metrics may not adequately capture the benefits of longer context windows. New metrics that assess reasoning ability, context awareness, and multi-document synthesis are needed. Future directions. Research is ongoing to address the challenges associated with long context windows and to further unlock their potential in Agentic RAG. Future directions include efficient attention mechanisms, developing novel attention mechanisms that can scale to very long sequences without compromising performance. Hierarchical context management, implementing hierarchical structures for organizing and prioritizing contextual information. Adaptive context window sizes, dynamically adjusting the context window size based on the complexity of the task and the available resources. Integration with external tools, combining long context windows with external tools and knowledge bases to further enhance agent capabilities. By carefully addressing these challenges and exploring these future directions, we can leverage the power of long context windows to create more powerful, efficient, and intelligent Agentic RAG systems. From vector databases to agentic knowledge graphs. We are at the forefront of knowledge management evolution, moving beyond simple data storage to intelligent, interconnected systems. Our expertise spans the spectrum, from leveraging the power of vector databases for semantic search and similarity analysis, to building sophisticated agentic knowledge graphs that actively reason and learn. Vector databases, semantic search and understanding. Vector databases have revolutionized how we understand and access information. By embedding data points into high-dimensional vector spaces, we unlock semantic search, find information based on meaning, not just keywords. Similarity matching, identify related concepts and items, revealing hidden connections. Personalized recommendations, deliver tailored experiences based on user profiles and preferences. Anomaly detection, identify outliers and unusual patterns in your data. We help you select the right vector database technology, example Pinecone, Weaviate, Milvus, and build robust pipelines for data embedding and querying, enabling you to derive actionable insights from unstructured data. Agentic knowledge graphs, intelligent reasoning and automation. Taking knowledge representation a step further, we build agentic knowledge graphs, aerodynamic networks of interconnected entities and relationships powered by intelligent agents. These agents can reason and infer, draw new conclusions based on existing knowledge, automate tasks, execute complex workflows and decision-making processes, learn and adapt, continuously improve their understanding of the domain, collaborate and communicate, interact with other agents and systems to achieve common goals. Agentic knowledge graphs enable truly intelligent applications across a range of industries, from scientific discovery and financial analysis to customer service and supply chain management. We provide end-to-end solutions, including knowledge graph design, agent development, and system integration. Our expertise. Our team comprises experts in natural language processing, NLP, machine learning, ML, knowledge representation and reasoning, KRR, database design and management, software engineering. Get in touch. Ready to transform your data into actionable intelligence. Contact us to discuss how vector databases and agentic knowledge graphs can unlock the full potential of your organization. Contact us. Testing and evaluating Agentic RAG performance metrics. Agentic RAG, Retrieval-Augmented Generation, systems combine the strengths of LLMs with the efficiency of information retrieval to answer complex queries, automate tasks, and provide insightful information. Thorough testing and evaluation are crucial to ensure these systems are reliable, accurate, and performant. Key performance metrics. We employ a multifaceted approach to evaluate Agentic RAG systems, focusing on the following key metrics. Accuracy, measures how factually correct and consistent the generated responses are. This includes evaluating for hallucinations and misinformation. Metrics include fidelity, the degree to which the generated response accurately reflects the information retrieved. Answer correctness, directly assesses whether the answer provided is correct based on ground truth. Relevance, assesses whether the retrieved documents and generated responses are pertinent to the user's query and task. Metrics include context relevance, measures how relevant the retrieved documents are to the query. Response relevance, measures how well the generated response addresses the query's intent. Efficiency, evaluates the speed and resource consumption of the system. Metrics include latency, measures the time taken to generate a response. Throughput measures the number of queries processed per unit of time. Cost considers the computational resources required for retrieval and generation. Coherence and fluency assesses the readability and naturalness of the generated responses. Metrics include grammatical correctness measures the grammatical accuracy of the generated text. Readability score assesses the ease with which the generated text can be understood. Grounding evaluates the system's ability to trace the source of information used in the generated response back to specific passages in the retrieved documents. This enhances trust and transparency. Task completion rate for Agentic RAG systems designed to perform tasks, this metric measures the percentage of tasks successfully completed. Testing methodologies. Our testing methodologies are designed to provide a comprehensive understanding of the system's performance across various scenarios. Benchmark datasets, we utilize publicly available and custom-built datasets to evaluate the system's performance on diverse queries and tasks. Adversarial testing, we employ adversarial examples to assess the system's robustness to noisy or misleading information. Human evaluation, we conduct human evaluations to assess the quality and usefulness of the generated responses from a user perspective. This includes A/B testing to compare different system configurations. Automated evaluation metrics, we leverage automated metrics, example Rouge, Blue, Meteor, to provide quantitative assessments of system performance. Ablation studies, we conduct ablation studies to understand the impact of different components on the system's overall performance. This helps in identifying critical areas for improvement. Tools and technologies. We utilize a variety of tools and technologies to facilitate testing and evaluation, including LLM evaluation frameworks, LangChain, LlamaIndex, and other frameworks for building and evaluating LLM-powered applications. Vector databases, FAIS, Pinecone, Chroma, and other vector databases for efficient document retrieval. Data analysis tools, Python libraries such as Pandas, NumPy, and Matplotlib for data processing and visualization. By rigorously testing and evaluating Agentic RAG systems, we aim to develop reliable and effective solutions that can address complex information needs and automate tasks with accuracy and efficiency. Scaling Agentic RAG for global enterprise deployment. Deploying Agentic Retrieval-Augmented Generation, RAG, systems at a global enterprise scale presents unique challenges. This section outlines key considerations and strategies for achieving robust, reliable, and performant RAG solutions across diverse geographic regions and organizational units. Key considerations for global scaling. Data localization and sovereignty, adhering to local data privacy regulations, example GDPR, CCPA, requires careful planning. Implement data residency strategies, potentially involving regional knowledge bases and localized agent configurations. Consider techniques like federated learning and differential privacy to enable global insights while respecting data boundaries. Knowledge graph distribution and synchronization, maintaining a consistent and up-to-date knowledge graph across geographically dispersed regions is crucial. Implement robust data synchronization mechanisms, potentially leveraging distributed database technologies or multi-master replication strategies. Consider using content delivery networks, CDNs, for faster knowledge retrieval. Agentic workflow orchestration, design agentic workflows that can dynamically adapt to different regional contexts. Implement role-based access control, RBAC, to ensure appropriate agent permissions and data access. Leverage workflow management systems that support distributed execution and monitoring. Language support and translation, cater to a global user base by supporting multiple languages. Integrate machine translation services for both user queries and retrieved knowledge. Consider using multilingual embeddings to improve cross-lingual retrieval accuracy. Infrastructure and resource allocation, strategically allocate computational resources, GPUs, CPUs, memory, across different regions to minimize latency and ensure optimal performance. Leverage cloud-based infrastructure for scalability and flexibility. Monitor resource utilization and dynamically adjust allocations as needed. Security and compliance, implement robust security measures to protect sensitive data and prevent unauthorized access. Conduct regular security audits and penetration testing to identify and address vulnerabilities. Ensure compliance with relevant industry regulations, example HIPAA, PCI DSS. Monitoring and observability, implement comprehensive monitoring and observability tools to track system performance, identify bottlenecks, and detect anomalies. Establish clear service level agreements, SLAs, and track key performance indicators, KPIs, such as response time, accuracy, and user satisfaction. Agentic role and responsibility definition, clearly define the roles and responsibilities of agents involved in the RAG pipeline. Ensure each agent has a specific purpose and limited scope to maintain control and reduce complexity. Strategies for effective global deployment. Microservices architecture, decompose the RAG system into independent microservices that can be deployed and scaled independently. This allows for greater flexibility and resilience. Containerization and orchestration, utilize containerization technologies, example Docker, and orchestration platforms, example Kubernetes, to automate deployment, scaling, and management of the RAG system. Caching strategies, implement aggressive caching strategies to reduce latency and improve performance. Leverage in-memory caches, content delivery networks, CDNs, and database caching mechanisms. Federated learning, train models across multiple regions without sharing raw data. This allows for global insights while respecting data sovereignty. A/B testing and experimentation, conduct A/B testing and experimentation to optimize the RAG system for different regions and user segments. Continuous integration and continuous delivery, CI/CD automate the build, test, and deployment process to ensure rapid and reliable releases. By carefully considering these factors and implementing appropriate strategies, organizations can successfully scale Agentic RAG systems for global enterprise deployment, unlocking the full potential of their knowledge assets and empowering users across the globe. How Agentic RAG simplifies financial report analysis. Financial report analysis is traditionally a complex and time-consuming process, often requiring specialized expertise to extract meaningful insights. The sheer volume of data, intricate accounting principles, and the need to identify subtle patterns can be daunting. Agentic Retrieval-Augmented Generation, RAG, offers a powerful solution to streamline and enhance this critical activity. The challenges of traditional financial report analysis. Data overload. Financial reports contain vast amounts of information, making it difficult to pinpoint relevant data points quickly. Subjectivity and bias. Human analysts may interpret information differently, leading to inconsistencies in analysis and potential biases. Time-consuming process. Manually sifting through reports and performing calculations can be extremely time-intensive. Limited scalability. Scaling traditional analysis methods to handle a growing number of reports and increasing complexity is challenging. Maintaining consistency. Ensuring consistent application of accounting principles and analytical methodologies across reports is difficult. Agentic RAG, a smarter approach. Agentic RAG leverages the power of large language models, LLMs, and intelligent agents to automate and augment financial report analysis. Here's how it simplifies the process. Automated data retrieval. Agentic RAG systems can automatically extract relevant data from financial reports, including key performance indicators, KPIs, financial ratios, and textual narratives. Agents are trained to understand financial terminology and structures, enabling precise data extraction. Contextual understanding. Unlike simple search algorithms, Agentic RAG utilizes LLMs to understand the context of the data. This allows it to identify relationships between different data points and provide deeper insights. The retrieval component ensures the LLM has the necessary context from the report itself. AI-powered analysis. LLMs can perform sophisticated analysis, such as trend identification, variance analysis, and risk assessment, with minimal human intervention. Personalized insights. Agentic RAG can tailor insights based on user-defined criteria and specific areas of interest. For example, a user can ask the system to analyze the company's cash flow statement and identify potential liquidity risks. Improved efficiency. By automating data retrieval and analysis, Agentic RAG significantly reduces the time and resources required for financial report analysis. Enhanced accuracy and consistency. AI-driven analysis minimizes human error and ensures consistent application of analytical methodologies across all reports. Actionable reporting. The system generates clear, concise, and actionable reports summarizing key findings and recommendations, enabling faster and more informed decision-making. Agents can also suggest next steps based on the analysis. Benefits of implementing Agentic RAG for financial report analysis. Increased efficiency and productivity. Improved accuracy and consistency. Deeper insights and better decision-making. Reduced costs and resource requirements. Enhanced scalability. Proactive risk management. Agentic RAG is transforming the landscape of financial report analysis, empowering organizations to unlock the full potential of their financial data and gain a competitive edge. Contact us to learn more about how Agentic RAG can benefit your organization. The role of reinforcement learning in Agentic Retrieval. Agentic Retrieval represents a paradigm shift in information access, moving beyond passive search to intelligent agents that actively learn and adapt to user needs. Reinforcement learning, RL, plays a crucial role in empowering these agents to optimize their retrieval strategies over time. Why reinforcement learning for Agentic Retrieval? Adaptive strategy optimization. Unlike traditional retrieval systems with fixed algorithms, RL enables agents to learn optimal retrieval policies through trial and error. By receiving rewards, example user satisfaction, relevance scores, and penalties, example irrelevant results, long search times, the agent gradually refines its actions to maximize long-term performance. Personalized retrieval experiences. RL allows agents to tailor retrieval strategies to individual users' preferences and search history. The agent can learn which types of queries, data sources, and interaction patterns are most effective for a particular user, leading to more relevant and satisfying results. Handling complex and dynamic environments. The information landscape is constantly evolving. RL enables agents to adapt to changes in data availability, user behavior, and search goals. They can continuously learn from new experiences and adjust their strategies accordingly. Exploration and exploitation of information sources. RL algorithms encourage agents to explore different information sources and retrieval techniques. This exploration phase is crucial for discovering new and potentially valuable resources that a predefined system might miss simultaneously. Agents exploit known effective strategies to provide reliable results. Key applications of RL in Agentic Retrieval. Query refinement and expansion. RL can be used to learn how to reformulate user queries to better match relevant documents. Agents can explore different query expansion techniques, example adding synonyms, related terms, and learn which ones lead to the best results. Source selection and ranking. In scenarios with multiple data sources, RL can help agents learn which sources are most likely to contain relevant information for a given query. The agent can also learn how to prioritize and rank these sources based on their historical performance. Interactive retrieval and dialogue systems. RL is particularly well suited for building interactive retrieval systems that engage in dialogue with users to clarify their information needs. The agent can learn how to ask effective questions and guide the user towards relevant information. Resource allocation and optimization. RL can be employed to optimize the allocation of computational resources, example time, memory, during the retrieval process. The agent can learn how to prioritize the most promising avenues of search and avoid wasting resources on irrelevant ones. Challenges and future directions. While RL offers significant potential for agentic retrieval, there are also challenges to address. These include reward engineering. Defining appropriate reward functions that accurately reflect user satisfaction and retrieval success is crucial for effective RL. Exploration-exploitation trade-off. Balancing the need to explore new retrieval strategies with the need to exploit known effective ones can be challenging. Scalability and efficiency. Training RL agents can be computationally expensive, especially in large and complex information environments. Explainability and interpretability. Understanding why an RL agent makes certain retrieval decisions is important for building trust and ensuring transparency. Future research directions include developing more efficient RL algorithms, exploring transfer learning techniques to leverage knowledge from related tasks, and incorporating human feedback to guide the learning process. As these challenges are addressed, RL is poised to play an increasingly important role in shaping the future of agentic retrieval and information access. Solving the needle in a haystack problem with Agentic RAG. Traditional Retrieval-Augmented Generation, RAG, systems often struggle to pinpoint specific, crucial information within vast datasets. The classic needle in a haystack problem. This limitation stems from their reliance on simple keyword-based retrieval, leading to irrelevant or noisy contexts that dilute the quality of generated responses. Agentic RAG overcomes these limitations by introducing intelligent agents that orchestrate the retrieval and generation processes. These agents are not just passive processors, they actively reason, plan, and adapt their approach based on the query and the characteristics of the data. Key benefits of Agentic RAG. Precision retrieval. Agents can leverage sophisticated techniques like semantic search, knowledge graph traversal, and context-aware filtering to identify the most relevant documents and passages with significantly improved accuracy. Multi-hop reasoning. Complex queries often require synthesizing information from multiple sources. Agentic RAG enables agents to perform multi-hop reasoning, iteratively retrieving and analyzing information to build a comprehensive understanding. Adaptive strategies. Agents can dynamically adjust their retrieval strategies based on the query and the nature of the retrieved information. This includes exploring different data sources, refining search queries, and prioritizing relevant content. Contextual understanding. Agents can leverage their understanding of the domain and the query to filter out irrelevant information and focus on the most important context, leading to more concise and accurate responses. Reduced hallucinations. By grounding the generation process in carefully selected and validated information, Agentic RAG minimizes the risk of generating inaccurate or fabricated content, hallucinations. How it works. Query understanding. The agent analyzes the user query to understand its intent, identify key concepts, and formulate a plan for retrieval. Iterative retrieval. Based on the plan, the agent retrieves relevant documents or passages from various data sources. This process may involve multiple iterations of refining the search query and exploring different information sources. Contextualization and filtering. The agent filters the retrieved information, removing irrelevant or noisy content and focusing on the most important context for the query. Knowledge integration. The agent integrates the retrieved information into a coherent and structured representation, often using knowledge graphs or other semantic models. Generation. The agent generates a response based on the integrated knowledge, ensuring accuracy, relevance, and conciseness. By leveraging the power of intelligent agents, Agentic RAG unlocks the full potential of large language models, enabling them to tackle complex information retrieval challenges and provide accurate, insightful, and contextually relevant answers to even the most demanding queries. Dynamic prompting techniques for Agentic RAG agents. This section explores advanced prompting strategies designed to elevate the performance of Retrieval-Augmented Generation, RAG, agents, specifically focusing on Agentic RAG architectures. Agentic RAG agents leverage dynamic prompting to adapt their behavior and knowledge retrieval based on the context of the user query and the evolving conversation. Key concepts and techniques. Contextual prompt engineering, crafting prompts that incorporate relevant conversation history, user preferences, and agent state to guide retrieval and generation processes. This ensures the agent stays aligned with the evolving conversation. Iterative refinement, employing prompts that encourage the agent to iteratively refine its answer based on initial retrieval results. This involves techniques like self-reflection and knowledge source validation. Adaptive retrieval strategies, using prompts to dynamically adjust the retrieval strategy based on the complexity of the query. For example, switching between keyword-based search and semantic search depending on the user's input. Knowledge source selection, implementing prompts that enable the agent to selectively choose the most appropriate knowledge sources from a pool of available resources. This requires the agent to evaluate the relevance and credibility of different sources. Multi-hop reasoning, designing prompts that guide the agent to perform multi-step reasoning by chaining together multiple retrieval and generation operations. This allows the agent to answer complex questions that require synthesis of information from different sources. Prompt augmentation with external tools, integrating prompts that allow the agent to utilize external tools, such as calculators or APIs, to enhance its reasoning and problem-solving capabilities. Benefits of dynamic prompting. Improved accuracy. By adapting to the context and iteratively refining its answers, the agent can provide more accurate and relevant information. Enhanced coherence. Dynamic prompting helps maintain coherence in long-form conversations by ensuring that the agent's responses are consistent with previous exchanges. Increased efficiency. Adaptive retrieval strategies can optimize the retrieval process, leading to faster response times and reduced computational costs. Greater flexibility. Dynamic prompting enables the agent to handle a wider range of user queries and adapt to different task requirements. Better user experience. By providing more personalized and context-aware responses, the agent can create a more engaging and satisfying user experience. Example use cases. Complex question answering, answering questions that require combining information from multiple documents and applying reasoning. Personalized recommendations, providing recommendations tailored to the user's preferences and past interactions. Automated report generation, generating reports that summarize key findings from a collection of documents. Code generation with dynamic context, assisting developers by generating code snippets based on the current codebase and project requirements. Explore the subsections below for detailed examples and practical implementations of these dynamic prompting techniques. Why Agentic RAG is essential for real-time data processing. In today's fast-paced digital landscape, organizations increasingly rely on real-time data processing to make informed decisions and stay competitive. Traditional Retrieval-Augmented Generation, RAG, struggles to keep pace with the dynamic nature of live data streams. Agentic RAG offers a critical evolution, providing the capabilities needed to effectively leverage real-time information. Challenges of traditional RAG with real-time data. Static knowledge base. Traditional RAG typically relies on a pre-indexed, static knowledge base. Updating this knowledge base to reflect real-time changes can be slow and cumbersome, leading to outdated responses. Limited contextual awareness. Traditional RAG often lacks the ability to dynamically adapt its retrieval strategy based on the changing context and user needs presented by real-time events. Inability to integrate external tools. Traditional RAG struggles to integrate with external tools and APIs necessary for accessing and processing real-time data from diverse sources. Passive information retrieval. Traditional RAG is passive, responding only to direct queries. It lacks the proactive ability to seek out and incorporate relevant real-time information based on ongoing events. Agentic RAG, a dynamic solution for real-time processing. Agentic RAG overcomes these limitations by introducing autonomous agents that can continuously monitor and update knowledge. Agents can proactively monitor real-time data streams, automatically updating the knowledge base with new information and insights. Dynamically adapt retrieval strategies. Agents can adjust their retrieval strategies based on the evolving context of real-time events, ensuring the most relevant information is retrieved. Integrate with external APIs and tools. Agents can seamlessly integrate with external APIs and tools to access and process data from a variety of real-time sources, such as news feeds, social media, and sensor data. Proactively gather information. Agents can actively seek out and incorporate relevant real-time information based on triggers and predefined rules, providing more comprehensive and up-to-date responses. Perform complex reasoning. Agents can reason over the retrieved information and combine it with their existing knowledge to provide more insightful and nuanced responses. Benefits of using Agentic RAG for real-time data. Improved accuracy. Provides more accurate and up-to-date responses by incorporating the latest real-time information. Enhanced relevance. Delivers more relevant information by dynamically adapting to the changing context of real-time events. Increased efficiency. Automates the process of monitoring, retrieving, and processing real-time data, freeing up human resources for more strategic tasks. Better decision-making. Enables more informed and data-driven decisions by providing access to comprehensive and timely insights. Competitive advantage. Allows organizations to react quickly to changing market conditions and gain a competitive edge. In conclusion, Agentic RAG is not just an improvement over traditional RAG, it's a necessity for organizations that want to effectively leverage the power of real-time data. By providing the ability to continuously monitor, process, and reason over live data streams, Agentic RAG empowers organizations to make faster, more accurate, and more impactful decisions. Integrating external APIs into your Agentic RAG pipeline. Agentic RAG, Retrieval-Augmented Generation, pipelines become significantly more powerful when integrated with external APIs. This integration allows your agent to not only retrieve and reason over internal or vectorized knowledge but also to access and utilize real-time data, perform actions, and interact with the external world. Benefits of API integration. Access to real-time data. Go beyond static knowledge bases. Query current weather conditions, stock prices, news headlines, or product inventory directly from their respective APIs. Enhanced action capabilities. Enable your agent to perform actions like sending emails, scheduling appointments, making purchases, or controlling IoT devices. Dynamic content generation. Create richer and more personalized responses by incorporating information fetched from APIs, tailored to the specific user query and context. Improved accuracy and contextual understanding. Augment the RAG process with external data to provide more accurate and relevant answers. For example, validating information retrieved from documents against a trusted external API. Automation of complex tasks. Chain together multiple API calls to automate intricate tasks, such as itinerary planning, lead generation, or financial analysis. Implementation considerations. API selection. Carefully choose APIs that are relevant to your application and offer reliable performance and data accuracy. API key management. Securely store and manage API keys to prevent unauthorized access. Employ best practices like environment variables or dedicated secret management systems. Rate limiting and error handling. Implement robust error handling to gracefully manage API rate limits, network issues, and unexpected responses. Consider using exponential backoff strategies for retries. Data transformation. Be prepared to transform the data received from APIs into a format that is compatible with your RAG pipeline. This may involve parsing JSON responses, cleaning data, and extracting relevant information. Security and privacy. Ensure that the integration of external APIs adheres to security best practices and protects user privacy. Consider data masking, anonymization, and encryption techniques. Prompt engineering. Craft prompts that effectively instruct the agent on when and how to utilize external APIs to fulfill user requests. Provide clear examples and instructions. Example use cases. Customer support. Integrate with CRM APIs to retrieve customer information and personalize responses. E-commerce. Access product inventory and pricing APIs to provide real-time product information. Travel planning. Integrate with flight and hotel booking APIs to help users plan their trips. Financial analysis. Utilize financial data APIs to provide market insights and investment recommendations. Content creation. Leverage news APIs to generate summaries and create engaging content. By strategically integrating external APIs, you can unlock the full potential of your Agentic RAG pipeline, enabling it to provide more accurate, informative, and actionable responses. The Developer Euro Trademark S Guide to Debugging Agentic RAG Loops. Agentic RAG, Retrieval-Augmented Generation, loops, where an agent iteratively refines its query, retrieves relevant information, and generates output, are powerful but complex. Debugging them requires a systematic approach. This guide provides developers with practical strategies and tools to effectively troubleshoot common issues and optimize performance. Understanding the challenges. Debugging Agentic RAG loops presents unique challenges. Opacity. The internal states and reasoning of the agent can be difficult to observe directly. Emergent behavior. Complex interactions between the agent, the knowledge base, and the generation model can lead to unexpected outcomes. Iterative nature. Errors can compound across iterations, making it hard to pinpoint the root cause. Context dependence. Performance can vary significantly depending on the input query and the content of the knowledge base. Debugging strategies. 1. Logging and tracing. Comprehensive logging is essential. Implement detailed logging at each stage of the loop. Query generation. Log the initial query and all subsequent reformulations. Include the agent's reasoning behind each query. Retrieval, log the retrieved documents, their relevance scores, and the retrieval query used. Generation, log the generated output at each iteration, including the prompts and the model's responses. Agent actions, log all actions taken by the agent, example generating a new query, generating a final answer, etc., with timestamps. Utilize tracing tools, example Langsmith, weights and biases, to visualize the entire loop execution and identify bottlenecks or error points. These tools often provide detailed performance metrics for each step. 2. Sanity checks and assertions. Incorporate sanity checks and assertions to validate intermediate results. Query validity, ensure that generated queries are well-formed and relevant to the task. Retrieval relevance, verify that retrieved documents are actually relevant to the query. Consider using metrics like precision and recall. Output format, check that the generated output adheres to the expected format, example JSON, Markdown. Value range, validate that numeric values, example scores, confidence levels, fall within reasonable ranges. Use assertions to catch unexpected errors early on in the development process. For example, assert that the retrieval process returns at least one document. 3. Unit testing. Isolate and test individual components of the loop. Query reformulation, test the agent's ability to generate relevant and effective queries based on different input scenarios. Retrieval system, evaluate the retrieval system's accuracy and efficiency using a held-out dataset. Generation model, test the generation model's ability to produce coherent and accurate output given specific prompts and retrieved documents. Mock external dependencies, example knowledge base, LLM API, to ensure consistent and repeatable test results. 4. Visualizations. Visualize the flow of information and dependencies within the loop. Knowledge graph, represent the relationships between entities and concepts in the knowledge base. Attention maps, if applicable, visualize the attention weights of the generation model to understand which parts of the input it is focusing on. Data flow diagrams, create diagrams illustrating the flow of data between different components of the loop. These visualizations can help identify patterns and relationships that are not apparent from logs or code alone. 5. Interactive debugging. Use interactive debugging tools, example Python debugger, Jupyter Notebook, to step through the loop execution and inspect variables at each stage. Modify parameters and code on the fly to experiment with different configurations and observe their effects. 6. Error analysis. When errors occur, perform a thorough analysis to identify the root cause. Identify the error point, pinpoint the exact step in the loop where the error originated. Analyze the inputs, examine the inputs to the failing step, including the query, retrieved documents, and agent state. Reproduce the error, create a minimal reproducible example to isolate the issue. Hypothesize and test, formulate hypotheses about the cause of the error and test them systematically. Common issues and solutions. Hallucinations, the model generates information that is not supported by the retrieved documents. Solution, improve retrieval accuracy, provide more context in the prompt, use a more reliable generation model. Consider adding a fact-checking mechanism. Query drift, the agent's queries become increasingly irrelevant over iterations. Solution, implement constraints on the query generation process, use a more robust query reformulation strategy, add a mechanism to reset the query to the original topic. Retrieval failure, the retrieval system fails to find relevant documents. Solution, improve the indexing and search capabilities of the knowledge base, refine the retrieval query, expand the knowledge base with more relevant information. Performance bottlenecks, the loop takes too long to execute. Solution, optimize the performance of the retrieval system and generation model, reduce the number of iterations, parallelize tasks where possible. Tools and libraries. LangChain, a framework for building and managing LLM-powered applications, including Agentic RAG loops. Langsmith, a platform for debugging, testing, and monitoring LangChain applications. Llama Index, a framework for building RAG applications with various data sources. Weights and biases, a platform for experiment tracking and model management. Best practices. Iterative development, start with a simple loop and gradually add complexity. Version control, use version control to track changes and facilitate rollbacks. Automated testing, implement a comprehensive suite of automated tests to ensure code quality and prevent regressions. Monitoring, continuously monitor the performance of the loop in production and identify areas for improvement. By following these guidelines, developers can effectively debug and optimize Agentic RAG loops, unlocking their full potential for a wide range of applications. Security best practices for Agentic RAG environments. Agentic RAG, Retrieval-Augmented Generation, environments present unique security challenges due to their autonomous nature and interaction with external knowledge sources. Implementing robust security measures is critical to protect sensitive data, prevent malicious activities, and maintain the integrity of the system. This section outlines key best practices for securing your Agentic RAG deployments. 1. Input validation and sanitization. Strict input controls, implement rigorous input validation to prevent prompt injection attacks and other forms of malicious input. Use whitelisting and blacklisting techniques to filter unauthorized characters and commands. Sanitize user input, sanitize all user-provided input before passing it to the retrieval and generation components. This includes escaping special characters and removing potentially harmful code. Content moderation, integrate content moderation tools to detect and filter harmful or inappropriate content generated by the agents, preventing the dissemination of misinformation or offensive material. 2. Secure retrieval and knowledge sources. Access control, implement strict access control measures for all knowledge sources, example databases, APIs, file systems, used by the RAG system. Limit access to only authorized agents and users. Data encryption, encrypt sensitive data at rest and in transit. Use strong encryption algorithms and manage encryption keys securely. Regular auditing, conduct regular security audits of knowledge sources to identify and address vulnerabilities. Source attestation, implement mechanisms to verify the authenticity and integrity of data retrieved from external sources. Consider using digital signatures or other cryptographic methods. 3. Agent behavior monitoring and control. Behavior monitoring, implement comprehensive monitoring of agent activities, including data access, API calls, and generated output. Detect and investigate any suspicious or anomalous behavior. Rate limiting and throttling, apply rate limiting and throttling mechanisms to prevent agents from overwhelming external resources or engaging in denial of service attacks. Sandboxing and isolation, run agents in isolated environments, example containers, virtual machines, to limit the impact of potential security breaches. Principle of least privilege, grant agents only the minimum necessary permissions required to perform their tasks. Avoid granting broad or unnecessary access. 4. API security. Authentication and authorization, enforce strong authentication and authorization mechanisms for all APIs used by the agents. Use industry standard protocols such as OAuth 2.0 or JWT. API rate limiting, implement rate limiting on API endpoints to prevent abuse and ensure availability. API security auditing, regularly audit API security configurations and logs to identify and address potential vulnerabilities. Input validation and output encoding, enforce strict input validation and output encoding to prevent injection attacks and other security vulnerabilities. 5. Logging and auditing. Comprehensive logging, implement comprehensive logging of all system activities, including user interactions, agent actions, API calls, and security events. Centralized logging, consolidate logs from all components of the RAG system into a central logging system for analysis and monitoring. Regular audits, conduct regular security audits of logs to identify and investigate potential security incidents. Retention policies, establish and enforce appropriate log retention policies to comply with regulatory requirements and security best practices. 6. Security updates and patch management. Regular updates, keep all software components of the RAG system up to date with the latest security patches. Vulnerability scanning, conduct regular vulnerability scanning to identify and address potential security vulnerabilities. Patch management process, establish a well-defined patch management process to ensure timely and effective patching of security vulnerabilities. 7. Human oversight and control. Human in the loop, implement a human in the loop mechanism to review and approve critical agent decisions, especially those involving sensitive data or significant consequences. Escalation procedures, establish clear escalation procedures for handling security incidents and suspicious activities. Training and awareness, provide security awareness training to all users and developers involved in the development and operation of the Agentic RAG system. By implementing these security best practices, you can significantly reduce the risk of security breaches and ensure the safe and responsible operation of your Agentic RAG environments. User intent classification in Agentic RAG systems. Understanding user intent is paramount for building effective and efficient Agentic Retrieval-Augmented Generation (RAG) systems. By accurately classifying the user's underlying goal, the system can optimize its retrieval strategy, generation process, and overall response. Why is user intent classification important? Improved relevance. Classifying intent allows the system to fetch more relevant documents, leading to higher quality answers. Optimized retrieval. Different intent types may require different retrieval methods, example keyword search versus semantic search. Enhanced generation, knowing the intent helps tailor the generated response to the user's specific needs, example providing a concise answer versus a detailed explanation. Agent orchestration, intent classification can guide the agent to select the most appropriate tool or sub-agent for handling the request. Personalization, understanding user intent enables personalization of the RAG system's behavior and responses over time. Classification approaches. We employ various techniques for user intent classification, including rule-based classification, using predefined rules based on keywords, patterns, and regular expressions to identify specific intents. Machine learning classification, training machine learning models, example support vector machines, naive Bayes, transformers, on labeled datasets to predict intent classes. Zero-shot and few-shot learning, leveraging pre-trained language models to classify intents with minimal or no training data. Hybrid approaches, combining rule-based and machine learning techniques for improved accuracy and robustness. Example intent categories. Typical user intent categories in Agentic RAG systems might include informational, seeking factual information or explanations. Navigational, trying to reach a specific resource or page. Transactional, aiming to complete a task or make a purchase. Conversational, engaging in a dialogue or seeking assistance. Comparative, comparing different options or products. Clarification seeking, requesting clarification on a previous response. Challenges and future directions. User intent classification in RAG systems faces several challenges, including ambiguity, user queries can be ambiguous and open to interpretation. Context sensitivity, intent can change based on the context of the conversation. Data scarcity, labeled data for specific domains or intent types may be limited. Evolving language, new slang, abbreviations, and terminology can emerge rapidly. Future research directions include improving robustness to ambiguous queries, developing more sophisticated context-aware models, exploring techniques for handling low-resource scenarios, integrating user feedback to continuously improve classification accuracy. How Agentic RAG improves customer support automation. Traditional customer support automation, powered by simple chatbots and basic retrieval-augmented generation (RAG), often struggles to handle complex or nuanced queries. Customers frequently encounter generic responses or are bounced between chatbots and human agents, leading to frustration and increased support costs. Agentic RAG represents a significant advancement by imbuing the RAG process with agency the ability to independently plan, execute, and adapt its actions to achieve specific goals. This translates to a more intelligent and effective customer support experience. Key benefits of Agentic RAG in customer support automation. Enhanced understanding of user intent. Unlike traditional RAG, Agentic RAG employs sophisticated natural language understanding (NLU) models to dissect the user's request, identifying the core problem, underlying context, and desired outcome. This goes beyond keyword matching to truly understand what the customer needs. Dynamic knowledge retrieval and synthesis. Instead of passively retrieving predefined chunks of information, Agentic RAG can proactively search across multiple knowledge sources, example FAQs, product manuals, internal wikis, CRM data, and synthesize relevant information into a coherent and personalized response. It can also identify and address knowledge gaps by formulating targeted search queries. Multi-step reasoning and problem solving. Complex issues often require multiple steps to resolve. Agentic RAG can break down complex queries into smaller, manageable subtasks, execute each step, and adapt its strategy based on the results. For example, it might first diagnose the problem, then suggest troubleshooting steps, and finally, offer alternative solutions. Personalized and contextualized responses. By leveraging user history, preferences, and current context, Agentic RAG can deliver highly personalized and relevant responses that address the customer's specific needs. This leads to a more satisfying and efficient support experience. Improved accuracy and reduced hallucinations. Agentic RAG incorporates mechanisms to verify the accuracy of retrieved information and minimize the risk of generating inaccurate or misleading responses, hallucinations. This is achieved through techniques like source attribution, knowledge graph reasoning, and human-in-the-loop validation. Seamless escalation to human agents. When Agentic RAG encounters a problem it cannot resolve, it can seamlessly escalate the issue to a human agent, providing them with a comprehensive summary of the interaction history and relevant context. This ensures a smooth and efficient handoff, minimizing customer frustration. How Agentic RAG works in practice. User input. The customer submits their query through a chatbot or other support channel. Intent understanding. The Agentic RAG system analyzes the user's query to understand their intent and extract relevant information. Knowledge retrieval. The system proactively searches across multiple knowledge sources to find relevant information. Reasoning and synthesis. The system reasons about the retrieved information and synthesizes it into a coherent response. Response generation. The system generates a personalized and contextualized response that addresses the customer's needs. Verification and validation. The system verifies the accuracy of the response and minimizes the risk of hallucinations. Response delivery. The system delivers the response to the customer. Escalation. If needed, if the system cannot resolve the issue, it seamlessly escalates it to a human agent. By adopting Agentic RAG, businesses can significantly enhance their customer support automation capabilities, improve customer satisfaction, reduce support costs, and empower human agents to focus on more complex and strategic tasks. Visualizing the thought process of an Agentic RAG system. Understanding the inner workings of an Agentic Retrieval-Augmented Generation (RAG) system can be challenging. This section provides visual representations of the system's thought process, enabling deeper insights into how it reasons, retrieves information, and generates responses. Interactive flow diagrams. Explore our interactive flow diagrams that illustrate the step-by-step execution of a RAG agent. These diagrams dynamically highlight the current stage, showcasing the data flow between the agent, the knowledge base, and the final output. Key components include observation and goal definition, how the agent interprets the user's query and formulates internal goals. Retrieval phase, the process of searching and selecting relevant documents from the knowledge base using different retrieval strategies. Visualizations may include query reformulation steps and similarity scores. Reasoning and planning, the agent's deliberation process, outlining the actions it plans to take based on the retrieved information. This includes task decomposition and sub-goal generation. Augmentation, how retrieved information is integrated into the prompt for the language model. Generation phase, the final response generation by the large language model, influenced by the augmented context. Reflection and iteration, if applicable, how the agent reflects on its performance and iteratively refines its approach for future queries. Visual analytics and dashboards. Access comprehensive dashboards that provide real-time analytics on the Agentic RAG system's performance. These dashboards display key metrics such as retrieval accuracy, measures the relevance and effectiveness of retrieved documents. Response quality, assesses the coherence, accuracy, and helpfulness of the generated responses. Latency, tracks the time taken for each stage of the RAG process, identifying potential bottlenecks. Token usage, monitors the consumption of tokens by the language model, allowing for cost optimization. Action execution log, provides a detailed record of the agent's actions and decisions, enabling auditability and debugging. Example trace visualizations. Examine specific examples of RAG system traces, showcasing the detailed thought process for various types of queries. These traces include the original user query, the agent's internal reasoning steps, the retrieved documents and their relevance scores, the augmented prompt sent to the language model, the final generated response. By visualizing the thought process of our Agentic RAG system, we aim to provide users with greater transparency, control, and understanding of its capabilities. This ultimately enables better collaboration and optimization of the system for specific applications. Choosing the right LLM for Agentic RAG, GPT-4 vs Claude vs Llama. Selecting the optimal large language model, LLM, is crucial for building effective Agentic Retrieval-Augmented Generation, RAG, systems. This section provides a comparative analysis of GPT-4, Claude, and Llama, highlighting their strengths and weaknesses in the context of Agentic RAG workflows. We consider factors such as reasoning capabilities, context window size, API accessibility, fine-tuning options, and cost-effectiveness to help you make an informed decision. Key considerations for LLMs in Agentic RAG. Reasoning and planning. Agentic RAG demands sophisticated reasoning to understand user intent, decompose complex tasks, and orchestrate the retrieval and generation processes. The LLM's ability to perform chain-of-thought reasoning and plan multi-step actions is paramount. Context window. A larger context window allows the agent to process more retrieved information and maintain a coherent understanding of the conversation history, enabling more accurate and contextually relevant responses. Retrieval capabilities. While RAG systems handle retrieval, the LLM influences how effectively retrieved information is leveraged. Its ability to synthesize information from various sources and identify relevant passages is critical. Tool use and API integration. Agentic systems often rely on external tools and APIs. The LLM's proficiency in understanding API specifications, generating correct API calls, and processing API responses is essential for seamless integration. Fine-tuning and customization. The ability to fine-tune the LLM on domain-specific data and agentic interaction patterns can significantly improve its performance in specific applications. Cost and performance trade-offs. Balancing the cost of API usage or model deployment with the desired level of performance is a key consideration, particularly for production-scale applications. GPT-4, the powerhouse. Strengths. GPT-4 excels in reasoning, planning, and complex task decomposition. Its strong general knowledge and powerful API integrations make it a versatile choice for a wide range of Agentic RAG applications. Its ability to understand nuanced instructions and generate coherent, human-like responses is unparalleled. Weaknesses. GPT-4 is generally the most expensive option. While its context window has improved, it can still be a limiting factor for very long documents or complex conversational histories. Fine-tuning can be costly and requires significant resources. Use cases: complex question answering, automated research, code generation, and applications requiring high levels of accuracy and reasoning. Claude, the conversational expert. Strengths: Claude shines in conversational contexts, exhibiting strong capabilities in understanding and maintaining conversational flow. Its long context window is a significant advantage for applications involving extensive dialogues or large documents. It is also known for its adherence to safety guidelines and its ability to avoid generating harmful or biased content. Weaknesses: while Claude's reasoning abilities are improving, they may not be as advanced as GPT-4 in certain domains. Its tool use capabilities and API integrations are generally considered less mature than GPT-4. Use cases: chatbots, customer service agents, long-form content generation, and applications requiring strong conversational skills and safety considerations. Llama, the open-source option. Strengths: Llama provides open-source access to powerful LLMs, allowing for greater control over the model and data. It offers fine-tuning capabilities, enabling customization for specific domains and tasks. It can be a cost-effective option for organizations with the resources to deploy and manage their own models. Weaknesses: Llama typically requires more computational resources and expertise to deploy and maintain than cloud-based API solutions. Its performance may vary depending on the specific variant and fine-tuning data. It often lacks the robustness and reliability of commercially supported models. Use cases: research, experimentation, domain-specific applications, and scenarios where data privacy or control are paramount. Decision Matrix, a simplified guide. This table provides a simplified comparison to guide your initial selection. The optimal choice depends on the specific requirements of your application. Feature: GPT-4 Claude Llama. Reasoning and planning excellent good, varies by variant. Context window large very large varies by variant. Tool use and API integration excellent good requires custom development. Fine-tuning yes, costly, yes, open source. Cost high moderate low, deployment costs. Ease of use high, API, low, requires deployment. Conclusion. The selection of the right LLM for your Agentic RAG system is a critical decision. Carefully evaluate your application's specific requirements, considering factors such as reasoning capabilities, context window size, API accessibility, fine-tuning options, and cost-effectiveness. Experiment with different models and fine-tune them to optimize performance for your specific use case. Regularly reevaluate your choice as LLM technology continues to evolve rapidly. The importance of recursive retrieval in Agentic RAG. Agentic Retrieval-Augmented Generation, RAG, elevates the capabilities of standard RAG systems by enabling autonomous agents to explore and synthesize information through iterative retrieval and generation. At the heart of this enhanced process lies recursive retrieval, a critical technique that empowers agents to overcome limitations inherent in traditional, single-hop retrieval approaches. Why recursive retrieval matters. Deeper contextual understanding. Traditional RAG often struggles with complex queries requiring multifaceted information. Recursive retrieval allows agents to refine their search queries based on initial retrieved results, progressively delving deeper into the knowledge base to build a more comprehensive understanding. Discovery of implicit relationships. Many valuable insights are hidden within implicit relationships between documents. By iteratively retrieving and analyzing related content, agents can uncover these connections, leading to more nuanced and insightful responses. Overcoming semantic drift. Single-hop retrieval can suffer from semantic drift, where the retrieved context deviates from the original query's intent. Recursive retrieval, with its iterative refinement, helps maintain focus and relevance, mitigating this risk. Improved answer quality and accuracy. The ability to explore information from multiple angles and validate findings through iterative retrieval significantly enhances the quality and accuracy of generated responses. Enhanced agent autonomy. Recursive retrieval empowers agents to independently navigate the knowledge base, adapt to unexpected information, and proactively seek out relevant context without constant human intervention. How it works. In a recursive retrieval process, the agent performs the following steps. Initial query. The agent begins with an initial query based on the user's input. Retrieval and analysis. Relevant documents are retrieved and analyzed for key information and potential follow-up queries. Query refinement. Based on the analysis of the retrieved documents, the agent refines the original query or formulates new, related queries. Iterative retrieval. Steps 2 and 3 are repeated iteratively, with each iteration building upon the previous findings. Synthesis and generation. Once the agent has gathered sufficient information, it synthesizes the findings and generates a response. Conclusion. Recursive retrieval is not merely an optimization, it is a fundamental shift in how RAG systems operate. By enabling agents to explore, refine, and validate information through iterative retrieval, it unlocks the true potential of Agentic RAG, leading to more intelligent, accurate, and insightful responses. As the complexity of tasks tackled by AI agents increases, the importance of recursive retrieval will only continue to grow. Advanced re-ranking strategies for Agentic AI agents. In the complex landscape of agentic AI, effectively re-ranking generated responses is crucial for ensuring relevance, accuracy, and user satisfaction. Our research and development focus on advanced re-ranking strategies that go beyond simple keyword matching or statistical measures. We leverage a combination of semantic understanding, contextual awareness, and agent-specific goals to optimize the final output. Key re-ranking techniques. Semantic similarity analysis. We employ state-of-the-art language models to understand the semantic relationships between candidate responses and the user's intent. This allows us to prioritize responses that address the underlying need, even if the exact keywords are absent. Contextual understanding and dialogue history. Our re-ranking algorithms incorporate the complete dialogue history and the broader context of the interaction. This ensures that responses are consistent with previous exchanges and contribute meaningfully to the overall goal. Agent-specific goal alignment. We tailor re-ranking strategies to the specific goals and capabilities of the agent. For example, an agent focused on information retrieval might prioritize responses with high factual accuracy and source credibility, while an agent designed for creative writing might favor originality and coherence. Relevance score aggregation and fusion. We combine multiple relevance scores derived from different sources, example semantic similarity, contextual fit, goal alignment, using sophisticated fusion techniques. This allows us to create a comprehensive ranking that reflects the diverse factors influencing response quality. Reinforcement learning for re-ranking optimization. We utilize reinforcement learning to continuously improve our re-ranking models based on user feedback and agent performance. This allows us to adapt to evolving user preferences and optimize for long-term success. Benefits of advanced re-ranking. Improved response quality. More relevant, accurate, and coherent responses lead to a better user experience. Enhanced user satisfaction. Users are more likely to be satisfied when the agent provides helpful and insightful responses. Increased agent effectiveness. By optimizing for specific goals, we enable agents to achieve their objectives more efficiently. Reduced latency. While advanced re-ranking adds a computational step, optimized algorithms minimize latency and maintain real-time responsiveness. Adaptability to diverse domains. Our re-ranking strategies are designed to be adaptable to a wide range of domains and agent types. Future directions. Our ongoing research focuses on exploring novel re-ranking techniques, including incorporating user preferences and personalization, tailoring re-ranking to individual user preferences based on historical data and explicit feedback. Leveraging knowledge graphs and external resources, integrating external knowledge sources to improve the accuracy and completeness of responses. Developing explainable re-ranking models, providing insights into the factors driving the ranking process, fostering trust and transparency. Contact us to learn more about how our advanced re-ranking strategies can enhance the performance of your agentic AI agents. Building an offline agentic RAG system for maximum privacy. In today's data-sensitive world, the need for AI solutions that prioritize privacy is paramount. Our focus is on creating fully offline, Agentic Retrieval-Augmented Generation, RAG, systems, ensuring complete data isolation and control. This approach is ideal for organizations handling sensitive information in industries like healthcare, finance, and legal, where external data exposure is strictly prohibited. Key features and benefits. Complete data isolation. Your data never leaves your environment. No reliance on external APIs or cloud services. Agentic capabilities. Our systems are powered by autonomous agents capable of complex reasoning, planning, and execution, exceeding the capabilities of standard RAG pipelines. Agents learn from internal knowledge and improve performance over time. Offline functionality. Operate independently of internet connectivity. Critical for secure environments and remote locations. Enhanced security. Mitigate data breaches and compliance risks associated with external API calls. Customizable and scalable, tailored to your specific data formats, workflows, and security requirements. Designed for seamless integration and growth. Reduced latency, faster response times compared to cloud-dependent RAG systems, especially in areas with limited bandwidth. Our approach. We employ a robust methodology for building offline agentic RAG systems. Data ingestion and preparation. Securely ingest, clean, and prepare your data for offline processing. We support a variety of data formats and implement rigorous data sanitization techniques. Embedding generation. Utilize locally hosted, open-source embedding models optimized for your specific domain to create vector representations of your data. No external APIs are used. Vector database implementation. Deploy a private vector database within your infrastructure to store and index the embeddings. This ensures fast and efficient retrieval of relevant information. We can support a variety of offline capable options. Agent design and training. Architect custom agents that can understand user queries, retrieve relevant information from the vector database, and generate insightful and accurate responses, all within the offline environment. We use techniques like reinforcement learning from human feedback, RLHF, with synthetic data to train these agents in a privacy-preserving manner. Evaluation and optimization. Thoroughly evaluate the system's performance and continuously optimize the models and agents using internal data and feedback. Secure deployment and monitoring. Deploy the system securely within your infrastructure and implement continuous monitoring to ensure its integrity and performance. Use cases. Internal knowledge base. Provide employees with secure and instant access to internal documentation, policies, and procedures. Secure data analysis. Analyze sensitive datasets without exposing them to external parties. Compliance and regulatory reporting. Generate accurate and compliant reports based on internal data, minimizing the risk of data breaches. Offline customer support. Enable customer support agents to answer inquiries accurately even without internet access. Confidential research and development. Support research activities that require strict data confidentiality. Contact us to discuss your specific requirements and discover how our offline agentic RAG system can empower your organization while ensuring maximum privacy and control over your data. How agentic RAG handles unstructured data at scale. Agentic Retrieval-Augmented Generation, RAG, offers a powerful solution for extracting insights from large volumes of unstructured data, going beyond the limitations of traditional RAG pipelines. At your company name, we've developed a robust Agentic RAG framework that excels in handling the complexity and variety inherent in unstructured data like text documents, PDFs, emails, and even audio/video transcripts. Key advantages of our Agentic RAG approach. Intelligent data segmentation and pre-processing. Our agents automatically analyze unstructured data and break it down into manageable chunks based on semantic meaning, not just fixed size segments. This ensures relevant information is grouped together for better retrieval and context. We employ techniques like named entity recognition, topic modeling, and dependency parsing to understand the underlying structure and relationships within the data. Adaptive retrieval strategies. Unlike static RAG systems, our agents dynamically choose the most appropriate retrieval strategy based on the query and the characteristics of the data. This includes employing different types of vector embeddings, keyword searches, and knowledge graph traversals to surface the most relevant information. We continuously refine our retrieval strategies through feedback loops and machine learning to optimize for accuracy and recall. Complex reasoning and inference. Our agents can perform multi-hop reasoning and inference to answer complex questions that require synthesizing information from multiple sources. They can understand context, identify relationships, and draw conclusions based on the retrieved data, providing more comprehensive and insightful answers. Automated knowledge graph construction and augmentation. Our system automatically extracts entities and relationships from unstructured data and populates a knowledge graph. This graph acts as a structured representation of the information, enabling more efficient and accurate retrieval. Furthermore, agents continuously monitor and update the knowledge graph with new information extracted from incoming data. Scalability and performance. Our Agentic RAG framework is designed for scale, leveraging distributed computing architectures and optimized indexing techniques to handle massive data sets. We continuously monitor performance and optimize our system to ensure low latency and high throughput. Human-in-the-loop validation. While our agents are highly autonomous, we incorporate human-in-the-loop validation to ensure accuracy and prevent hallucinations. Experts can review and refine the agent's reasoning process and the generated responses, improving the overall quality of the system. Example applications. Customer support automation, analyzing customer interactions, emails, chat logs, call transcripts, to provide personalized and accurate responses to customer inquiries. Compliance and risk management, identifying and extracting relevant information from regulatory documents and internal policies to ensure compliance. Market research and competitive intelligence, monitoring news articles, social media feeds, and competitor websites to gain insights into market trends and competitive landscapes. Scientific discovery, accelerating research by analyzing scientific publications and patents to identify new research directions and potential breakthroughs. Ready to unlock the power of your unstructured data? Contact us to learn how our Agentic RAG solution can help you gain a competitive advantage. The intersection of Agentic RAG and knowledge graph embeddings. This section explores the powerful synergy between Agentic Retrieval-Augmented Generation, RAG, systems and knowledge graph embeddings, KGEs. By combining the strengths of both approaches, we unlock new possibilities for building more intelligent, adaptable, and insightful AI applications. Harnessing knowledge graph embeddings for enhanced RAG. Traditional RAG systems often rely on keyword-based or semantic similarity searches over large text corpora. However, this can sometimes lead to retrieving irrelevant or incomplete information. Integrating KGEs into the RAG pipeline addresses this limitation by semantic understanding. KGEs capture the rich relationships and entities within a knowledge graph, enabling a deeper semantic understanding of the query and the available knowledge. Improved retrieval. KGEs facilitate more precise retrieval by considering not only the literal terms of the query but also related entities and relationships within the knowledge graph. This includes finding information that is implicitly related but not directly stated in the query. Contextual awareness. By providing a structured representation of knowledge, KGEs offer valuable context to the RAG system, allowing it to generate more relevant and coherent responses. Reasoning capabilities. KGEs enable the RAG system to perform basic reasoning tasks, such as inferring new relationships or identifying inconsistencies in the retrieved information. Agentic RAG empowered by knowledge graphs. Agentic RAG takes the traditional RAG approach further by incorporating autonomous agents that can dynamically plan, retrieve, and synthesize information from various sources. Knowledge graphs and their embeddings play a crucial role in this process. Guiding agent behavior. KGEs can inform the agent's decision-making process by providing a structured representation of the knowledge domain and identifying relevant entities and relationships to explore. Facilitating multi-hop reasoning. Agents can leverage KGEs to navigate complex knowledge graphs, performing multi-hop reasoning to discover deeper connections and extract more insightful information. Improving explainability. By tracing the agent's reasoning path within the knowledge graph, we can gain a better understanding of how the system arrived at its conclusions, enhancing transparency and explainability. Supporting complex task decomposition. KGEs can aid in breaking down complex user queries into smaller, more manageable tasks for the agent, leading to more efficient and effective information retrieval. Use cases. The combination of Agentic RAG and KGEs has numerous potential applications, including question answering systems, answering complex, multifaceted questions that require reasoning over structured and unstructured data. Drug discovery, identifying potential drug targets and understanding drug-disease relationships. Financial analysis, detecting fraud, predicting market trends, and managing risk. Personalized recommendations, providing more relevant and personalized recommendations based on user preferences and knowledge graph insights. Looking ahead. The integration of Agentic RAG and KGEs is a rapidly evolving field with significant potential. Future research directions include developing more sophisticated KGE models that can capture complex relationships and temporal dynamics. Exploring new methods for integrating KGEs into the agent's planning and decision-making processes. Improving the explainability and trustworthiness of these systems. Streamlining academic research with Agentic RAG tools. Academic research demands efficiency and accuracy. Researchers often face the daunting task of sifting through vast amounts of information to extract relevant insights. Agentic Retrieval-Augmented Generation, RAG, tools offer a powerful solution to this challenge, significantly streamlining the research process. What are Agentic RAG tools? Unlike traditional search engines, Agentic RAG tools combine the strengths of retrieval systems with the generative capabilities of large language models, LLMs. These intelligent agents are designed to automatically retrieve relevant information from diverse sources, including academic databases, preprint servers, and institutional repositories. Reason over retrieved data to identify key concepts, relationships, and supporting evidence. Synthesize information into coherent and comprehensive summaries tailored to specific research questions. Iteratively refine search strategies based on initial results and user feedback, leading to more precise and relevant findings. Benefits for academic researchers. Accelerated literature reviews, quickly identify and summarize relevant research papers, saving valuable time. Enhanced information synthesis, combine information from multiple sources to generate comprehensive overviews of specific topics. Improved research question refinement, gain a deeper understanding of existing research, enabling more focused and impactful research questions. Reduce bias, access a broader range of perspectives and research findings, mitigating potential biases in traditional search methods. Increased collaboration, facilitate knowledge sharing and collaborative research efforts through centralized access to synthesized information. Applications in academic disciplines. Agentic RAG tools are applicable across a wide range of academic disciplines, including science and engineering, analyzing experimental data, identifying research gaps, and predicting potential outcomes. Social sciences, exploring social trends, conducting policy analysis, and synthesizing qualitative data. Humanities, examining historical documents, analyzing literary works, and identifying thematic patterns. Medicine and healthcare, reviewing clinical trial data, identifying drug interactions, and personalizing treatment plans. Getting started with Agentic RAG. We offer a range of resources and support to help researchers integrate Agentic RAG tools into their workflow. This includes workshops and training sessions, learn how to effectively utilize Agentic RAG tools for academic research. Customizable toolkits, adapt our pre-built agents to your specific research needs. Consultation services, receive expert guidance on designing and implementing Agentic RAG solutions. Contact us today to learn more about how Agentic RAG tools can transform your academic research and unlock new possibilities. Reducing false positives in retrieval with Agentic verification. In Retrieval-Augmented Generation, RAG, systems, a critical challenge is the occurrence of false positives, irrelevant or incorrect information retrieved and subsequently used by the language model. This leads to inaccurate or misleading outputs, undermining the system's reliability and usefulness. Agentic verification offers a powerful solution to mitigate this issue. What is Agentic verification? Agentic verification employs a second, independent agent specifically designed to scrutinize the information retrieved by the primary retrieval system. This agent acts as a verifier, employing diverse strategies to assess the relevance, accuracy, and trustworthiness of the retrieved content. It can cross-reference information, compare retrieved information with multiple sources to identify inconsistencies or contradictions. Apply reasoning and logical inference, evaluate the plausibility of the retrieved information based on common knowledge and established facts. Assess source credibility, evaluate the trustworthiness and reliability of the sources from which the information was retrieved. Employ specialized knowledge, utilize specific knowledge domains or tools to validate the information's accuracy. Benefits of Agentic verification. Improved accuracy, significantly reduces the number of false positives passed to the language model, leading to more accurate and reliable outputs. Enhanced relevance, ensures that only the most relevant information is used, improving the contextuality and focus of the generated content. Increased trustworthiness, provides users with more confidence in the system's outputs by filtering out potentially misleading or inaccurate information. Reduced hallucinations, by verifying the retrieved information, the likelihood of the language model generating hallucinations based on incorrect information is minimized. Scalability, Agentic verification can be implemented as an automated process, making it scalable for handling large volumes of retrieval requests. Implementation considerations. Implementing Agentic verification requires careful consideration of several factors. Agent design, the verification agent should be specifically designed for the task, with appropriate knowledge, reasoning capabilities, and access to relevant resources. Verification strategies, the agent should employ a diverse range of verification strategies tailored to the specific domain and type of information being retrieved. Performance trade-offs, balancing the accuracy of the verification process with the computational cost is crucial for achieving optimal performance. Integration with RAG pipeline, seamless integration with the existing RAG pipeline is essential for efficient and effective verification. Conclusion. Agentic verification is a promising approach for reducing false positives in retrieval-augmented generation systems. By adding an independent layer of scrutiny to the retrieval process, it can significantly improve the accuracy, relevance, and trustworthiness of the generated outputs, leading to more reliable and valuable AI applications. We are actively researching and developing advanced agentic verification techniques to further enhance the performance of our RAG systems. Agentic RAG for software documentation, a better way to search. Software documentation can be vast and complex. Traditional search methods often return irrelevant or overwhelming results, leaving developers frustrated and wasting valuable time. Agentic Retrieval-Augmented Generation, RAG, offers a superior solution by leveraging the power of AI to understand user intent and provide targeted, actionable answers directly from your documentation. What is Agentic RAG? Agentic RAG goes beyond simple keyword matching. It combines the strengths of retrieval, intelligent search and retrieval of relevant documentation chunks based on semantic understanding, not just keywords. Augmentation, enriching the retrieved context with additional information, such as code examples, related articles, and cross-references. Generation, using a large language model, LLM, to synthesize the retrieved and augmented information into a concise and contextually relevant answer. Agentic behavior, an autonomous agent guides the entire process, iteratively refining the retrieval, augmentation, and generation steps based on the user's initial query and the evolving context. This includes asking clarifying questions, exploring related topics, and proactively addressing potential follow-up needs. Benefits of Agentic RAG for software documentation. Improved search accuracy. Semantic understanding leads to more relevant results, reducing the time spent sifting through irrelevant information. Contextualized answers. Receive answers tailored to your specific question, including relevant code snippets, examples, and links. Reduce time to resolution. Find answers faster, allowing developers to focus on building and innovating. Enhanced developer experience. A more intuitive and efficient documentation experience leads to increased developer satisfaction and productivity. Proactive problem solving. The agent can anticipate potential issues and provide solutions before they become problems. Reduce support costs. By empowering developers to self-serve, Agentic RAG can significantly reduce the burden on support teams. Key features. Semantic search. Understands the meaning behind your query, not just the keywords. Contextual awareness. Takes into account the surrounding information and the user's intent. Interactive Q&A. Engages in a conversation to clarify the user's needs and provide more accurate answers. Code example integration. Seamlessly integrates code examples into the answers. Knowledge graph integration. Leverages a knowledge graph to understand relationships between concepts and provide more comprehensive information. Continuous learning. Adapts and improves over time based on user feedback and interactions. Ready to experience the future of software documentation search? Contact us to learn how Agentic RAG can transform your documentation into a powerful resource for your developers. Enhancing sentiment analysis through Agentic context retrieval. Traditional sentiment analysis often struggles with nuances, sarcasm, and contextual dependencies in text. To overcome these limitations, we've developed a novel approach incorporating Agentic context retrieval, ACR. This method leverages autonomous agents to intelligently explore and retrieve relevant contextual information that significantly enriches the accuracy and depth of sentiment analysis. How Agentic context retrieval works. Agent initialization. An agent is initialized with the target text, the text to be analyzed, and an objective, to gather context that might influence or clarify the sentiment expressed. Iterative exploration. The agent autonomously explores relevant data sources, example news articles, social media feeds, knowledge graphs, or even past conversations, using search queries tailored to the target text. The agent dynamically adjusts its search strategy based on the information already gathered. Contextual information gathering. The agent identifies and extracts potentially relevant snippets of text or structured data. It assesses the relevance of each piece of information based on predefined criteria and a learned understanding of sentiment indicators. Contextual integration. The retrieved context is then integrated with the original text to create a richer, more informed representation. This integrated representation is used as input to the sentiment analysis model. Sentiment prediction. A state-of-the-art sentiment analysis model, fine-tuned on contextually enriched data, predicts the sentiment of the target text. Benefits of using Agentic context retrieval. Improved accuracy. By incorporating relevant context, ACR significantly improves the accuracy of sentiment analysis, especially in cases of sarcasm, irony, or domain-specific language. Enhanced understanding. ACR provides a deeper understanding of the reasons behind the expressed sentiment, allowing for more insightful analysis. Adaptive learning. The agent learns from its interactions and progressively refines its search strategies, leading to continuous improvement in context retrieval. Reduced false positives/negatives. Contextual information helps disambiguate potentially misleading words or phrases, reducing the likelihood of inaccurate sentiment classification. Explainable insights. The retrieved context provides transparency into the factors influencing the sentiment prediction, making the results more explainable and trustworthy. Applications. Our Agentic context retrieval approach can be applied in a wide range of applications, including brand monitoring, understanding customer sentiment towards a brand by considering context from social media, reviews, and news articles. Financial analysis, analyzing market sentiment by considering news articles, company reports, and expert opinions. Social media analysis, identifying trending topics and understanding public opinion by considering contextual information from related posts and comments. Customer service, automatically identifying and prioritizing urgent customer requests based on the expressed sentiment and context of their messages. Learn more. Contact us to learn more about how our Agentic context retrieval can enhance your sentiment analysis capabilities. Link to Contact Us page. The economics of Agentic RAG. Is the performance worth the cost? Agentic Retrieval-Augmented Generation, RAG, represents a significant advancement in AI, offering potentially superior performance compared to traditional RAG systems. However, this enhanced capability comes with increased computational and development costs. This section delves into the economic considerations of deploying Agentic RAG, helping you assess whether the performance gains justify the investment for your specific use case. Understanding the cost drivers. The economics of Agentic RAG are complex and multifaceted. Key cost drivers include model complexity and size. Agentic RAG often relies on larger and more sophisticated language models, LLMs, for planning, reflection, and tool use. These models require more computational resources, driving up inference costs. Inference compute. The iterative and multi-step nature of agentic reasoning necessitates more inference calls than traditional RAG. Each interaction with the LLM incurs a cost, particularly with commercial APIs. Data storage and indexing. Efficient retrieval in Agentic RAG depends on well-structured and easily accessible knowledge sources. Building and maintaining these knowledge bases, including vector databases, involves storage and indexing costs. Prompt engineering and fine-tuning. Designing effective prompts for agents to perform complex tasks requires significant experimentation and expertise. Fine-tuning LLMs for specific domains or tasks further adds to the development costs. Tool development and integration. Agentic RAG systems often require integration with external tools and APIs. Developing and maintaining these integrations incurs both development and operational costs. Monitoring and evaluation. Rigorous monitoring and evaluation are crucial for ensuring the reliability and safety of Agentic RAG systems. This includes tracking performance metrics, detecting biases, and mitigating potential risks. Analyzing performance gains. Before investing in Agentic RAG, it's crucial to quantify the potential performance improvements compared to simpler RAG approaches. Consider the following metrics. Accuracy and completeness. Does Agentic RAG deliver more accurate and complete answers to complex queries? Reasoning and problem solving. Can the system perform more sophisticated reasoning and problem solving tasks? Efficiency and throughput. Despite higher inference costs, does the agentic approach ultimately improve efficiency by automating tasks or reducing human intervention? User satisfaction. Does the improved performance translate to higher user satisfaction and engagement? Making the ROI calculation. To determine whether the performance of Agentic RAG justifies the cost, conduct a thorough return on investment (ROI) analysis. This involves estimating total costs, accurately project all development, operational, and infrastructure costs associated with deploying and maintaining an Agentic RAG system. Quantifying potential benefits. Identify and quantify the potential benefits, such as increased revenue, reduced operational costs, improved customer satisfaction, or enhanced decision-making. Calculating ROI. Use standard ROI formulas to compare the potential benefits to the total costs. Consider intangible benefits. Factor in intangible benefits like improved brand reputation, increased innovation, or enhanced competitive advantage. Conclusion. Agentic RAG offers exciting possibilities for enhancing AI-powered applications. However, a careful economic assessment is essential to ensure that the performance gains justify the increased costs. By understanding the cost drivers, quantifying the potential benefits, and conducting a thorough ROI analysis, you can make informed decisions about whether Agentic RAG is the right solution for your specific needs. How to handle ambiguous queries in Agentic RAG pipelines. Ambiguous queries pose a significant challenge in Retrieval-Augmented Generation (RAG) pipelines, particularly within agentic systems. These queries lack sufficient clarity, making it difficult for the system to determine the user's precise intent and retrieve the most relevant context for generation. Effective handling requires a multifaceted approach, combining robust query understanding, strategic context retrieval, and intelligent response generation. Strategies for addressing ambiguity. Query reformulation and clarification. Active clarification. The agent can actively engage the user to refine their query. This involves asking clarifying questions like, are you interested in topic A or topic B, or could you provide more details about entity X? Implicit clarification. Analyze the user's query history or profile to infer their likely intent. For example, if a user previously asked about electric cars, a subsequent query for charging might be interpreted as referring to electric car charging. Query expansion. Use techniques like synonym expansion, hypernym/hyponym extraction, and semantic similarity to broaden the query and capture related concepts. This helps ensure relevant documents are retrieved even if the initial query was too narrow. Multi-document retrieval and ranking. Diverse retrieval strategies. Implement multiple retrieval strategies using different query formulations, embeddings, or search engines. This increases the likelihood of capturing relevant information from various perspectives. Contextual ranking. Employ a ranking mechanism that prioritizes documents based on their relevance to all possible interpretations of the ambiguous query. Models trained for multi-intent retrieval can be particularly effective. Fine-grained context chunking. Break down retrieved documents into smaller, more manageable chunks. This allows the agent to focus on the most relevant passages for each potential interpretation. Agentic reasoning and decision-making. Intent recognition. Utilize a dedicated intent recognition module to identify the user's likely intent, S, from the ambiguous query. This module can leverage machine learning models trained on large datasets of user queries. Plan selection. Based on the identified intent, S, the agent can select an appropriate action plan. For example, if the user's intent is unclear, the agent might choose a plan that involves asking clarifying questions. Adaptive response generation. Generate responses that acknowledge the ambiguity and address multiple potential interpretations. This can involve presenting multiple options, summarizing information from different perspectives, or guiding the user towards a more specific query. Utilizing knowledge graphs and external resources. Entity disambiguation. Link entities mentioned in the query to corresponding entries in a knowledge graph. This helps resolve ambiguity around entities with multiple meanings or related concepts. Fact verification. Leverage external knowledge sources, example APIs, databases, to verify information and resolve conflicting interpretations. Example scenario. Consider the ambiguous query, what about Apple? This could refer to Apple Incorporated, the technology company, Apple's, the fruit, or even the Apple Records label. An Agentic RAG pipeline could address this as follows. Intent recognition. The system identifies multiple potential intents, company, fruit, record label. Clarification. Optional, the agent might ask, are you interested in Apple Incorporated, the technology company, Apple's, the fruit, or something else? Retrieval. The system retrieves documents related to all three potential interpretations. Ranking. Documents are ranked based on their relevance to each interpretation. Response generation. The agent generates a response that addresses all likely intents. For example, Apple can refer to Apple Incorporated, the technology company known for iPhones and Macs, or Apple's, the fruit. Which are you interested in learning more about? Conclusion. Handling ambiguous queries in Agentic RAG pipelines requires a strategic combination of query understanding, context retrieval, and intelligent reasoning. By employing the techniques described above, developers can build more robust and user-friendly systems that effectively address ambiguous requests and provide accurate and relevant information. The rise of specialized agents in RAG ecosystems. Retrieval-Augmented Generation, RAG, is rapidly evolving, moving beyond simple question answering to complex workflows that require nuanced understanding and task execution. A key driver of this evolution is the emergence of specialized agents within the RAG ecosystem. What are specialized agents? Specialized agents are autonomous AI entities designed to perform specific functions within a RAG pipeline. Unlike monolithic RAG systems, these agents are modular, focusing on particular aspects of retrieval, generation, or post-processing. This specialization leads to improved performance, efficiency, and maintainability. Key advantages of specialized agents. Enhanced accuracy, focusing on specific tasks allows agents to be fine-tuned for optimal performance in their domain. For example, a dedicated query rewriting agent can improve retrieval accuracy by reformulating user queries for better semantic matching. Improved efficiency, by breaking down complex tasks into smaller, more manageable components, specialized agents can significantly reduce latency and computational costs. Increased flexibility, modularity allows for easy adaptation to changing requirements. New agents can be added or existing agents can be modified without disrupting the entire system. Better explainability, individual agents are easier to understand and debug than monolithic systems, leading to increased transparency and trust. Scalability, scaling individual agents to meet specific demand is more efficient than scaling an entire RAG pipeline. Examples of specialized agents in RAG. Query Understanding Agent, analyzes user intent and extracts key entities and relationships from the query. Document Retrieval Agent, searches a knowledge base or external data sources to identify relevant documents. Contextualization Agent, filters and prioritizes retrieved documents based on their relevance to the user query. Answer Generation Agent, formulates an answer based on the retrieved context and the user query. Fact Verification Agent, validates the generated answer against reliable sources to ensure accuracy. Formatting Agent, presents the answer in a user-friendly format. The future of RAG, a multi-agent ecosystem. The future of RAG lies in building sophisticated multi-agent systems where specialized agents collaborate to solve complex tasks. These systems will leverage orchestration frameworks and communication protocols to enable seamless interaction between agents, resulting in more powerful, versatile, and intelligent RAG applications. As the field continues to advance, we can expect to see the development of more sophisticated and specialized agents, further pushing the boundaries of what RAG can achieve. Fine-tuning LLMs for better performance in Agentic RAG. Agentic RAG, Retrieval-Augmented Generation, empowers LLMs to autonomously retrieve and integrate relevant information, resulting in more accurate and insightful responses. However, leveraging the full potential of this approach often requires fine-tuning the LLM itself. This section explores the benefits, techniques, and considerations for fine-tuning LLMs to enhance performance within Agentic RAG systems. Why fine-tune for Agentic RAG? Improved relevance. Fine-tuning can teach the LLM to better identify truly relevant information from the retrieved documents, filtering out noise and irrelevant passages. This leads to more focused and accurate responses. Enhanced information integration. A fine-tuned LLM can seamlessly blend retrieved knowledge with its pre-existing knowledge, creating a cohesive and natural-sounding response. It learns how to effectively synthesize information from diverse sources. Task-specific optimization. By fine-tuning on data representative of the specific tasks the Agentic RAG system will handle, example answering medical queries, summarizing legal documents, you can tailor the LLM's performance for optimal results in that domain. Agentic skill improvement. Fine-tuning can improve the LLM's abilities to plan its actions, example choosing which documents to retrieve, monitor its progress, and revise its strategies based on retrieved information. This leads to more effective and intelligent agent behavior. Fine-tuning techniques. Several techniques can be employed to fine-tune LLMs for Agentic RAG. Supervised fine-tuning, SFT. This involves training the LLM on a dataset of input queries, relevant retrieved documents, and desired output responses. SFT helps the LLM learn to generate high-quality responses given relevant contextual information. Reinforcement learning from human feedback, RLHF uses human preferences to guide the LLM's learning process. Human annotators provide feedback on the quality of the LLM's responses, which is then used to train a reward model. The LLM is then fine-tuned to maximize this reward. Data augmentation, creating synthetic data by modifying existing examples or generating new ones can help expand the training dataset and improve the LLM's robustness. This is particularly useful when limited labeled data is available. Techniques include back translation, prompt augmentation and knowledge graph-based augmentation. Adversarial training. This approach involves training the LLM to defend against adversarial examples, which are designed to mislead the model. This can improve the LLM's robustness and generalization ability. Considerations for effective fine-tuning. Data quality. The quality of the fine-tuning data is crucial. Ensure that the data is accurate, relevant, and representative of the tasks the Agentic RAG system will handle. Invest time in cleaning and curating the data. Dataset size. A sufficiently large dataset is needed for effective fine-tuning. The size of the dataset will depend on the complexity of the task and the size of the LLM. Hyperparameter tuning. Experiment with different hyperparameters, such as learning rate, batch size, and number of epochs, to optimize the LLM's performance. Evaluation metrics. Carefully select evaluation metrics that accurately reflect the desired performance goals. Metrics such as Rouge, Blue, and human evaluation can be used. Also consider metrics that assess the reasoning ability and factual correctness of the responses. Regularization. Employ regularization techniques to prevent overfitting, especially when fine-tuning on limited data. Continuous monitoring. Continuously monitor the performance of the fine-tuned LLM and retrain as needed to maintain optimal performance. Tools and resources. Several tools and resources are available to facilitate fine-tuning LLMs for Agentic RAG, including Hugging Face Transformers, a widely used library for working with LLMs, providing tools for training, evaluating, and deploying models. DeepSpeed and FairScale, distributed training frameworks that enable efficient fine-tuning of large LLMs. Commercial LLM APIs, example OpenAI, Google AI often provide fine-tuning services with varying levels of customization. By carefully considering these techniques and considerations, you can effectively fine-tune LLMs to significantly improve the performance of Agentic RAG systems, enabling them to generate more accurate, informative, and insightful responses. Overcoming the context window limits with agentic chunking. Large language models, LLMs, possess remarkable capabilities, but their performance is often constrained by the finite size of their context windows. This limitation impacts their ability to process and reason over extensive documents, engage in long-form conversations, and access knowledge from vast information repositories. Agentic chunking offers a novel approach to address this challenge by intelligently breaking down large inputs into manageable chunks and enabling an agent to selectively retrieve and utilize only the most relevant information within the context window. What is agentic chunking? Agentic chunking is a sophisticated method that combines intelligent document splitting, chunking, with an agent-based retrieval mechanism. Instead of simply dividing documents into arbitrary segments, agentic chunking analyzes the content and structure to create meaningful and self-contained chunks. The agent then acts as a smart selector, deciding which chunks are most pertinent to the current query or task, effectively simulating long-term memory and overcoming context window limitations. Key advantages of agentic chunking. Enhanced contextual understanding. By preserving semantic relationships within chunks, the LLM can better understand the overall context and nuances of the information. Improved retrieval efficiency. The agent efficiently identifies and retrieves the most relevant chunks, reducing noise and improving the accuracy of LLM responses. Scalability and long-term memory. Agentic chunking enables LLMs to handle much larger documents and engage in longer conversations without being limited by the immediate context window. Reduced hallucinations. By focusing on relevant information and filtering out extraneous details, agentic chunking helps to minimize the risk of hallucinations and generate more accurate and reliable outputs. Customization and adaptability. The chunking and retrieval strategies can be tailored to specific domains and tasks, allowing for optimal performance in various applications. How it works. Document analysis. The input document is analyzed to identify key sections, paragraphs, and sentences. Intelligent chunking. The document is split into chunks based on semantic boundaries and context, aiming to create self-contained and meaningful segments. Agent implementation. An agent is designed to manage and retrieve chunks. This agent can leverage various techniques like semantic search, knowledge graphs, or even a trained LLM to determine the relevance of each chunk to the current query. Selective retrieval. The agent selects the most relevant chunks based on the user's query or the current state of the conversation. Contextual integration. The selected chunks are combined and fed into the LLM, providing it with the necessary context to generate a response or complete the task. Applications of agentic chunking. Long-form question answering. Answering complex questions based on large documents or collections of documents. Document summarization. Generating concise and informative summaries of lengthy texts. Chatbots and conversational AI. Enabling chatbots to maintain context and engage in more natural and extended conversations. Code generation and completion. Providing LLMs with the context necessary to generate accurate and complete code snippets. Knowledge base management. Efficiently searching and retrieving information from large knowledge bases. Agentic chunking represents a significant advancement in overcoming the limitations of LLM context windows. By combining intelligent chunking with agent-based retrieval, it unlocks the potential for LLMs to process and reason over vast amounts of information, paving the way for more powerful and versatile AI applications. Designing intuitive user interfaces for Agentic RAG apps. Agentic RAG, Retrieval-Augmented Generation, applications are revolutionizing how users interact with information and AI. However, their complexity demands carefully crafted user interfaces, UI, to ensure accessibility, efficiency, and a positive user experience. This section outlines key considerations and best practices for designing intuitive UIs for Agentic RAG applications. Understanding the user context. Before designing, deeply understand your target audience. Consider their technical proficiency. Are they comfortable with AI concepts or do they require simplified explanations? Domain expertise. How familiar are they with the subject matter the application addresses? Specific goals. What tasks are they trying to accomplish using the application? Tailoring the UI to their needs will significantly improve usability and adoption. Key UI elements and considerations. 1. Clear query input and control. Provide users with clear and intuitive methods for formulating their queries. This includes natural language input, support free-form text input. Structured queries, if applicable, offer structured query options for users who prefer more control, example filters, facets. Query history, allow users to easily access and reuse previous queries. Contextual help, provide helpful tips and examples within the input field. Stop button, allow users to interrupt long-running processes. 2. Transparent retrieval and generation process. Demystify the RAG process by providing insights into how the application is working. This fosters trust and understanding. Source attribution, clearly identify the sources used to generate the response. Link directly to the original documents whenever possible. Confidence scores, optional, consider displaying confidence scores for the retrieved information or generated responses. This helps users assess the reliability of the output. Intermediate steps, optional for advanced users, consider showing the steps the agent takes to retrieve and generate the response. This can include the search queries used, the documents retrieved, and the reasoning process. 3. Concise and actionable responses. The generated responses should be clear, concise, and directly address the user's query. Focus on summarization, present information in a summarized format, highlighting key findings. Actionable insights, go beyond simply providing information and offer actionable recommendations based on the retrieved knowledge. Formatting, use clear formatting, example bullet points, headings, tables, to improve readability. 4. Iterative refinement and feedback loops. Encourage users to provide feedback on the accuracy and relevance of the responses. This helps improve the application's performance over time. Feedback mechanisms, implement simple feedback mechanisms, such as thumbs up or thumbs down buttons, or a form for more detailed feedback. Iteration options, allow users to easily refine their queries based on the initial response. For example, provide suggested follow-up questions or options to broaden or narrow the search. 5. Visualizations, where appropriate. Consider using visualizations to present information in a more engaging and understandable way. This is particularly useful for data summarization. Visualizations can help users quickly grasp trends and patterns in large data sets. Knowledge graphs, visualize the relationships between different concepts and entities. Interactive exploration, allow users to explore the data and knowledge graph through interactive visualizations. Accessibility considerations. Ensure your UI is accessible to all users, including those with disabilities. Follow accessibility guidelines such as WCAG, Web Content Accessibility Guidelines. Key considerations include semantic HTML. Use semantic HTML tags to provide structure and meaning to your content. Keyboard navigation. Ensure that all elements are accessible using the keyboard. Screen reader compatibility. Design your UI to be compatible with screen readers. Color contrast. Use sufficient color contrast to ensure that text is readable. Testing and iteration. Regularly test your UI with real users to identify usability issues and areas for improvement. Use A/B testing to compare different design options and optimize for performance. Iterate on your design based on user feedback and testing results. By focusing on user needs, providing transparency, and embracing iterative refinement, you can design intuitive UIs that unlock the full potential of Agentic RAG applications. Agentic RAG in education, personalized learning assistance. Imagine a learning environment where every student has a personalized AI tutor, capable of adapting to their individual learning styles, pace, and knowledge gaps. Agentic Retrieval-Augmented Generation, RAG, is making this a reality, offering powerful capabilities for creating highly effective personalized learning assistance, PLAS. What is Agentic RAG and why is it revolutionary for education? Traditional RAG systems retrieve relevant information from a knowledge base and then use a language model to generate answers. Agentic RAG takes this a step further by empowering the system with agency. This means the PLA can actively seek information. Instead of passively responding to queries, the PLA can formulate its own questions, explore different data sources, textbooks, research papers, online resources, and identify relevant information even if the student doesn't know exactly what to ask. Reason and plan. The PLA can break down complex topics into smaller, manageable steps, create personalized learning paths, and adjust its teaching strategy based on the student's progress. Monitor progress and adapt. By tracking student responses, identifying areas of difficulty, and providing targeted feedback, the PLA continuously adapts its approach to maximize learning outcomes. Collaborate with students. The PLA can engage in interactive dialogues, provide hints, offer alternative explanations, and even simulate real-world scenarios to enhance understanding. Key benefits of Agentic RAG-powered PLAS. Personalized learning paths, tailored curricula based on individual student needs and learning styles. Improved knowledge retention, active learning and personalized feedback lead to deeper understanding and better retention. Increased engagement, interactive and dynamic learning experiences keep students motivated and engaged. Scalable support, provides access to high-quality tutoring for all students, regardless of background or location. Reduced teacher workload, automates repetitive tasks, freeing up teachers to focus on individual student needs and more complex instructional activities. Applications in education. Agentic RAG PLAS can be used in a variety of educational settings. Homework help, provides step-by-step guidance and explanations for homework assignments. Test preparation, creates personalized study guides and practice questions based on individual learning gaps. Language learning, offers interactive language practice and personalized feedback on pronunciation and grammar. Subject tutoring, provides in-depth explanations and support for challenging subjects like math, science, and history. Skill development, helps students develop critical thinking, problem solving, and research skills. The future of education is personalized and AI-powered. Agentic RAG represents a significant leap forward in personalized learning, offering the potential to transform education and empower students to reach their full potential. By providing individualized support, fostering engagement, and adapting to individual needs, Agentic RAG PLAS are paving the way for a more effective and equitable learning experience for all. Bridging the gap between structured and unstructured data with agents. Organizations are drowning in data, but often struggle to leverage its full potential. The challenge lies in the disconnect between structured data, typically residing in databases and easily queried, and unstructured data, such as text documents, emails, images, and audio files, which require more sophisticated processing. Our intelligent agents provide a powerful solution to bridge this gap. By employing cutting-edge natural language processing, NLP, computer vision, and machine learning, ML, techniques, these agents can extract meaningful insights, automatically identify key entities, relationships, and sentiments within unstructured data. Structure unstructured data, transform free-form text and multimedia into structured formats suitable for analysis and integration with existing databases. Automate data enrichment, enhance structured data with relevant information extracted from unstructured sources, creating a more comprehensive and contextualized view. Facilitate cross-data analytics, enable powerful analytics that combine insights from both structured and unstructured data, revealing hidden patterns and opportunities. Improve decision-making, provide data-driven insights that support more informed and strategic decision-making across the organization. Key capabilities. Custom agent development, we tailor agents to your specific data sources, business needs, and industry requirements. Scalable infrastructure, our agents are designed to handle large volumes of data with high efficiency and reliability. Secure data processing, we prioritize data security and privacy, implementing robust security measures throughout the data processing pipeline. Real-time data integration, seamlessly integrate processed data with your existing systems and workflows. Continuous learning, our agents continuously learn and improve their performance based on new data and feedback. Benefits. Enhanced data utilization, unlock the value hidden within your unstructured data. Improved operational efficiency, automate data extraction and processing tasks, freeing up valuable resources. Faster time to insights, accelerate the process of gaining actionable insights from your data. Competitive advantage, make data-driven decisions that give you a competitive edge in the market. Ready to unlock the full potential of your data? Contact us to learn more about how our intelligent agents can help you bridge the gap between structured and unstructured data. The role of memory in long-term agentic RAG conversations. In Retrieval-Augmented Generation, RAG, systems, especially those designed for long-term, agentic conversations, memory plays a pivotal role in enabling coherent, context-aware, and personalized interactions. Unlike simple RAG pipelines that operate on isolated queries, Agentic RAG systems leverage memory to maintain a persistent understanding of the conversation history, user preferences, and evolving goals. This allows them to maintain contextual consistency. By storing and recalling previous turns in the conversation, the agent can understand the nuances of user requests and avoid repetitive or contradictory responses. This is crucial for building trust and rapport over extended interactions. Personalized responses. Memory allows the system to learn user preferences, example preferred tone, specific knowledge domains, past successful strategies, and tailor its responses accordingly. This leads to a more engaging and effective user experience. Plan and execute complex tasks. Agentic systems can break down complex goals into smaller, manageable subtasks. Memory is essential for tracking the progress of these subtasks, managing dependencies, and adjusting the plan based on new information or user feedback. Reduce latency and improve efficiency. By caching frequently accessed information and relevant knowledge retrieved from external sources, memory can significantly reduce the need for repetitive retrieval operations, resulting in faster response times and reduced computational cost. Enable learning and adaptation. Memory facilitates the continuous learning and adaptation of the agent over time. By analyzing past interactions, the system can identify areas for improvement in its retrieval strategies, response generation techniques, and overall task execution. Several memory mechanisms can be employed in Agentic RAG systems, including conversation buffers, storing a fixed number of recent turns in the conversation. Simple and effective for maintaining short-term context. Summarization techniques, condensing the conversation history into a concise summary, allowing the agent to retain the core context while minimizing memory usage. Knowledge graphs, representing the entities, relationships, and events extracted from the conversation in a structured format. This allows for efficient retrieval of relevant information and reasoning about the conversation's underlying semantics. Vector databases, embedding the conversation history and user profiles into vector representations, enabling similarity search and retrieval of relevant information based on semantic similarity. Choosing the appropriate memory mechanism and architecture depends on the specific application requirements, the complexity of the tasks, and the available computational resources. Effective memory management is critical for building robust, reliable, and engaging Agentic RAG systems that can handle long-term conversations with users. Optimizing embedding models for Agentic retrieval tasks. Agentic retrieval tasks, where AI agents autonomously search for and leverage information to achieve goals, demand highly optimized embedding models. Simply using off-the-shelf models often results in suboptimal performance due to the nuanced requirements of agent interaction and decision-making. Key challenges in Agentic retrieval. Contextual understanding. Agents need to understand the context of their current task and subsequent queries, requiring embeddings to capture not just keyword relevance but also semantic relationships and agent-specific knowledge. Multi-hop reasoning. Agents often need to chain together information from multiple sources to arrive at an answer. Embedding models must support efficient retrieval across these diverse information hops. Dynamic information landscapes. The information landscape can change rapidly. Embedding models need to be adaptable to new information and maintain accuracy over time. Actionable insights. Agents require information that can be directly translated into actions. Embeddings must prioritize actionable insights over purely informational snippets. Scalability and efficiency. As agents handle increasingly complex tasks, embedding models must scale efficiently without sacrificing retrieval accuracy or introducing latency. Optimization strategies. We offer a range of strategies to optimize embedding models specifically for agentic retrieval. Fine-tuning with agent-specific data. Fine-tuning pre-trained models with datasets derived from agent interactions, including successful and failed retrieval attempts, significantly improves performance on target tasks. This includes incorporating agent-specific vocabulary and task-relevant knowledge. Contrastive learning with task-specific negatives. Generating challenging negative examples based on the specific goals of the agent leads to more robust and discriminative embeddings. We employ techniques like hard negative mining and adversarial training. Reinforcement learning for embedding refinement. Training embedding models using reinforcement learning, where the reward signal is based on the agent's performance in downstream tasks, allows for continuous optimization based on real-world interactions. Multimodal embedding techniques, integrating information from various modalities, such as text, images, and code, can provide a more comprehensive understanding of the information landscape and improve retrieval accuracy for agents operating in diverse environments. Knowledge graph integration. Enriching embeddings with knowledge graph information allows agents to leverage structured knowledge and perform more sophisticated reasoning tasks. Specialized indexing and search techniques. Utilizing efficient indexing and search algorithms, such as approximate nearest neighbor and search, can significantly improve retrieval speed and scalability, especially for large-scale knowledge bases. Our expertise. Our team possesses deep expertise in embedding models, agentic systems, and machine learning optimization techniques. We work closely with our clients to understand their specific needs and develop customized solutions that deliver significant performance improvements in agentic retrieval tasks. Contact us to learn more about how we can help you optimize your embedding models for agentic success. How Agentic RAG facilitates cross-language information retrieval. Agentic Retrieval-Augmented Generation, RAG, significantly enhances cross-language information retrieval, CLIR, by addressing the limitations of traditional methods. Traditional CLIR often relies on machine translation, MT, as a pre-processing step, which can introduce noise and inaccuracies, impacting retrieval performance. Agentic RAG offers a more nuanced and effective approach. Key benefits of Agentic RAG for CLIR. Reduced reliance on imperfect translation. Instead of directly translating the entire query or document corpus, Agentic RAG can leverage multiple specialized agents with distinct capabilities. Some agents can focus on identifying key entities and concepts in the source language query, while others can focus on semantic understanding and information extraction from the target language documents. This modular approach minimizes the impact of translation errors in less critical aspects of the text. Dynamic adaptation and contextual awareness. Agentic RAG systems can dynamically adapt their retrieval strategy based on the complexity of the query and the characteristics of the target language corpus. For example, for queries requiring deep contextual understanding, the system can engage a reasoning agent to infer relationships and context. This adaptability improves retrieval accuracy and relevance. Improved relevance ranking. By employing agents specializing in relevance assessment and semantic similarity, Agentic RAG can more effectively rank documents in the target language based on their relevance to the original query's intent. This goes beyond simple keyword matching and considers the semantic relationships between concepts. Multilingual knowledge integration. Agents can be designed to access and integrate information from various multilingual knowledge bases, enriching the retrieval process. This allows the system to provide answers that are not explicitly stated in the target language documents but are logically inferred from multilingual knowledge resources. Enhanced explainability. Agentic RAG systems offer improved explainability in their retrieval process. By tracking the actions and reasoning steps of each agent, it is possible to understand why a particular document was retrieved, providing valuable insights into the system's decision-making process. Example scenario. Imagine a user querying what are the health benefits of matcha in English and needing information from a Japanese medical database. Instead of simply translating the query, an Agentic RAG system might. An entity recognition agent identifies matcha and health benefits as key entities. A semantic understanding agent analyzes the query's intent to find positive health effects. A Japanese document retrieval agent retrieves relevant documents in Japanese, potentially using translated keywords or semantic embeddings. An information extraction agent extracts key health benefits mentioned in the Japanese documents. A synthesis agent combines the extracted information and presents it to the user in English, possibly augmented with information from English language knowledge bases about matcha. Conclusion. Agentic RAG represents a significant advancement in CLIR, offering improved accuracy, relevance, and explainability compared to traditional MT-based approaches. By strategically deploying specialized agents, these systems can overcome the limitations of language barriers and provide users with access to a wider range of information from diverse linguistic sources. Automating regulatory compliance checks with Agentic RAG. Staying compliant with ever-evolving regulations is a constant challenge for businesses. Manual processes are time-consuming, prone to errors, and difficult to scale. Our innovative solution leverages Agentic Retrieval-Augmented Generation, RAG, to automate and streamline your regulatory compliance checks, saving you time and resources while minimizing risk. How Agentic RAG works for compliance. Document ingestion and indexing. Our system securely ingests and indexes your critical documents, including internal policies, procedures, and relevant regulatory guidelines from various sources, example SEC, FINRA, GDPR. Agentic question answering. Instead of simple keyword searches, our AI agents understand the nuanced meaning of your compliance inquiries. They break down complex questions into smaller, manageable tasks. Retrieval from diverse sources. Agents intelligently retrieve relevant information from indexed documents, public databases, and even external APIs, ensuring comprehensive coverage. Reasoning and inference. Agents utilize advanced reasoning capabilities to connect disparate pieces of information and draw conclusions about compliance status. Generation of compliance reports. The system automatically generates clear, concise, and auditable compliance reports that highlight potential risks and provide actionable recommendations. Continuous monitoring and updates. Stay ahead of the curve with continuous monitoring of regulatory changes. The system automatically updates its knowledge base and alerts you to any potential impact on your operations. Key benefits. Reduce compliance costs, automate manual tasks and free up your compliance team to focus on strategic initiatives. Improved accuracy, minimize human error and ensure consistent application of regulatory requirements. Enhanced efficiency, accelerate compliance checks and reduce the time it takes to generate reports. Proactive risk mitigation, identify potential compliance gaps early and take corrective action before issues arise. Scalability and adaptability, easily scale your compliance efforts as your business grows and adapts to new regulations. Centralized compliance knowledge base, create a single source of truth for all your compliance-related information. Use cases. Financial services, anti-money laundering, AML, know your customer, KYC, Dodd-Frank compliance. Healthcare, HIPAA compliance, data privacy regulations. Manufacturing, environmental regulations, safety standards. Technology, GDPR compliance, data security regulations. Ready to transform your regulatory compliance process? Contact us today to learn more about how Agentic RAG can help your organization achieve and maintain compliance with ease. The paradox of choice, how agents select relevant chunks. In the age of information overload, intelligent agents face a significant challenge, sifting through vast quantities of data to identify the most relevant information for a given task. This process often involves breaking down large datasets into smaller, manageable chunks and then selecting the subset that best addresses the agent's objective. This is where the paradox of choice comes into play. The paradox of choice, as articulated by Barry Schwartz, suggests that while having more options might seem beneficial, it can actually lead to increased anxiety, decision paralysis, and decreased satisfaction. Agents, much like humans, can become overwhelmed when faced with too many potential chunks of information, leading to inefficient processing and suboptimal outcomes. Key considerations for chunk selection. Relevance scoring. Implementing robust relevance scoring mechanisms is crucial. This involves assigning a score to each chunk based on its probability of contributing to the agent's goal. Techniques like TF-IDF, cosine similarity, and semantic embeddings can be used to quantify relevance. Filtering and prioritization. Employing filters to eliminate irrelevant chunks based on predefined criteria, example keywords, data sources, timestamps, can significantly reduce the search space. Prioritization algorithms can then rank the remaining chunks based on their relevance scores. Cognitive load management. Agents need strategies to manage their cognitive load. This could involve techniques like incremental processing, where chunks are processed in batches, or using heuristics to quickly narrow down the options. Contextual awareness. Understanding the context in which the agent is operating is vital. The same chunk of information might be highly relevant in one context but irrelevant in another. Contextual awareness allows the agent to dynamically adjust its selection criteria. Exploration versus exploitation, striking a balance between exploring new, potentially relevant chunks and exploiting known, high-value chunks is essential. Exploration can uncover novel information, while exploitation ensures that the agent leverages its existing knowledge effectively. By understanding and addressing the paradox of choice, we can design more efficient and effective intelligent agents that are capable of navigating the complexities of information overload and delivering optimal results. Further research. Adaptive chunking strategies. How can agents dynamically adjust their chunking strategies based on the characteristics of the data and the task at hand? Reinforcement learning for chunk selection. Can reinforcement learning be used to train agents to select the most relevant chunks of information over time? Human-agent collaboration. How can we design systems that allow humans and agents to collaborate effectively in chunk selection tasks? Implementing feedback loops in Agentic RAG systems. Agentic Retrieval-Augmented Generation, RAG, systems represent a significant leap forward in AI-driven knowledge access and generation. By combining the reasoning capabilities of autonomous agents with the contextual grounding provided by RAG, these systems can tackle complex tasks with improved accuracy and adaptability. However, their effectiveness hinges on a crucial component: feedback loops. Why feedback loops are essential? Without well-defined feedback mechanisms, Agentic RAG systems can suffer from drift, deviating from desired behavior over time due to accumulating errors or biases. Brittle responses, failing to generalize well to unseen inputs or changing environments. Suboptimal performance, remaining stuck in local optima without learning from past experiences. Feedback loops address these challenges by providing a continuous stream of information that guides the system towards better performance. They enable the system to refine its retrieval strategies, learning which information sources are most relevant and reliable for specific tasks. Improve its generation quality, producing more accurate, coherent, and contextually appropriate outputs. Optimize its agentic planning, developing more effective strategies for breaking down complex tasks into manageable steps. Types of feedback loops. We can categorize feedback loops in Agentic RAG systems into several key types. Explicit user feedback, direct feedback from users, example ratings, thumbs up/down, free text reviews, indicating the quality or relevance of the system's responses. This is often the most valuable form of feedback but can be sparse and subjective. Implicit feedback, derived from user behavior patterns, example click-through rates, dwell time on specific content, subsequent actions taken. Implicit feedback provides a more continuous and less intrusive signal of user satisfaction. Model-based feedback, utilizing other AI models, example reward models, critique models, to evaluate the system's outputs based on predefined criteria such as accuracy, fluency, and safety. This allows for automated and scalable assessment. Environmental feedback, observing the real-world consequences of the system's actions and using this information to adjust its behavior. This is particularly relevant in applications where the system interacts with a dynamic environment. Internal feedback, monitoring internal system metrics, example retrieval confidence scores, generation perplexity, task completion rates, to identify areas for improvement. This allows for self-monitoring and optimization. Implementing feedback loops, key considerations. Effective implementation of feedback loops requires careful planning and execution. Key considerations include data collection, establishing mechanisms for collecting relevant feedback data from various sources. Feedback processing, cleaning, normalizing, and aggregating feedback data to create a consistent and meaningful signal. Model training, using feedback data to update the system's retrieval, generation, and planning components. Evaluation metrics, defining appropriate metrics to measure the impact of feedback loops on system performance. Iteration and experimentation, continuously experimenting with different feedback strategies and evaluating their effectiveness. Conclusion. Feedback loops are not just an add-on feature, they are fundamental to the long-term success of Agentic RAG systems. By embracing a feedback-driven development approach, we can create more intelligent, adaptable, and reliable AI solutions that effectively leverage knowledge to solve complex problems. A comparative study of Agentic RAG frameworks in 2026. This section presents a comprehensive comparative analysis of prominent Agentic Retrieval-Augmented Generation, RAG, frameworks as they stand in 2026. Building upon the advancements observed in knowledge retrieval, large language model, LLM, integration, and autonomous agent development, we evaluate several key frameworks across a range of performance metrics, architectural designs, and applicability to diverse use cases. Methodology. Our study employs a rigorous methodology encompassing both quantitative and qualitative assessments. We focus on frameworks demonstrating robust capabilities in complex reasoning, multi-step planning, and dynamic knowledge integration. The evaluation process involves benchmark datasets, utilizing established benchmark datasets, example improved versions of HotPotQA, DROP, and new benchmarks focusing on longitudinal reasoning and adaptation, to measure factual accuracy, reasoning depth, and contextual understanding. Performance metrics, evaluating frameworks based on key metrics such as answer precision, recall, F1 score, latency, resource consumption, GPU utilization, memory footprint, and robustness to noisy or incomplete data. Architectural analysis, deconstructing the internal architecture of each framework to identify key components, including retrieval mechanisms, knowledge graph integration, agent coordination strategies, and self-improvement mechanisms. Case studies, applying the frameworks to real-world scenarios such as automated research, personalized content generation, and complex problem-solving within specific domains, example financial analysis, medical diagnosis. Ethical considerations, assessing the potential for bias amplification, misinformation generation, and other ethical concerns associated with each framework. Frameworks under review. This study examines the following leading Agentic RAG frameworks. Framework A name, example Meta's ARIA Advanced Brief Description of Framework A, highlighting its strengths and weaknesses. Framework B name, example Google's Adaptive Retrieval Network Brief Description of Framework B, highlighting its strengths and weaknesses. Framework C name, example OpenAI's Cognitive Synergy Platform Brief Description of Framework C, highlighting its strengths and weaknesses. Framework D name, Example: a leading open source community framework. Brief description of framework D, highlighting its strengths and weaknesses. Note: framework names are placeholders and should be replaced with actual framework names relevant to 2026. Key findings. Our preliminary findings indicate significant advancements in the ability of Agentic RAG frameworks to handle complex, multifaceted queries and adapt to evolving knowledge landscapes. However, challenges remain in areas such as explainability, robustness to adversarial attacks, and mitigation of bias. A detailed report outlining specific performance results and architectural comparisons will be released in Q4 2026. Future directions. Based on our findings, we identify several key areas for future research and development in the field of Agentic RAG, including developing more robust and explainable reasoning engines, improving the ability to dynamically adapt to new information and changing environments, enhancing mechanisms for mitigating bias and ensuring fairness, exploring the integration of diverse knowledge sources and modalities, creating more efficient and scalable architectures for deployment in resource-constrained environments, harnessing the power of small language models in Agentic RAG. Agentic Retrieval-Augmented Generation, RAG, is rapidly evolving, moving beyond simple query answering to complex, multi-step reasoning and action. While large language models, LLMs, often dominate the conversation, small language models, SLMs, offer compelling advantages in specific Agentic RAG scenarios. The strategic advantage of SLMs. SLMs, when strategically deployed, can significantly enhance Agentic RAG systems by improved efficiency and cost-effectiveness. SLMs require significantly less computational resources, leading to lower infrastructure costs and faster inference times, especially crucial for real-time applications and high-volume processing. Enhanced specialization and fine-tuning. SLMs can be more easily fine-tuned on specific domain knowledge or task-specific datasets. This leads to superior performance in niche areas where generic LLMs may struggle. Think of a specialized SLM for extracting entities from financial documents or triaging customer support tickets. Reduce latency and edge deployment. The smaller footprint of SLMs allows for edge deployment on devices with limited resources, enabling faster response times and offline functionality. This is invaluable for applications like robotic process automation or mobile assistance. Increased explainability and control. SLMs often provide greater transparency into their decision-making processes, making it easier to debug and optimize the agent's behavior. This is especially important in regulated industries requiring auditability. Privacy considerations. Processing sensitive data with on-premise SLMs can enhance data privacy and security compared to relying on cloud-based LLM services. Architecting Agentic RAG with SLMs. Effectively integrating SLMs into Agentic RAG requires careful architectural considerations. Key strategies include hybrid architectures. Combining the strengths of both SLMs and LLMs is a powerful approach. Use SLMs for pre-processing, filtering, or routing tasks, while leveraging LLMs for more complex reasoning or generation steps. Knowledge distillation. Train SLMs to mimic the behavior of larger LLMs, transferring knowledge and capabilities to a more efficient model. Modular agent design. Break down complex tasks into smaller, manageable modules, assigning specific SLMs to handle each module based on their expertise. Reinforcement learning. Train SLMs to optimize their actions within the Agentic RAG environment, improving their ability to achieve specific goals. Conclusion. SLMs are not simply scaled-down LLMs, they represent a powerful alternative for building efficient, specialized, and controllable Agentic RAG systems. By strategically leveraging their strengths, developers can unlock new possibilities and push the boundaries of what's possible with intelligent agents. Improving retrieval precision with Agentic hypothesis generation. In the realm of information retrieval, achieving high precision ensuring that retrieved results are relevant and accurate remains a significant challenge. Traditional keyword-based search often falls short, yielding irrelevant or noisy results. To address this, we are exploring a novel approach, Agentic hypothesis generation, AHG. What is Agentic hypothesis generation? AHG leverages the power of intelligent agents, specifically large language models, LLMs, to proactively generate hypotheses related to a user's query before initiating the retrieval process. Instead of relying solely on keywords, our system employs agents to interpret the query intent. Agents analyze the nuances of the user's query, understanding the underlying information need and potential subtopics. Generate relevant hypotheses. Based on the interpreted intent, agents formulate a range of plausible hypotheses that could answer the query. These hypotheses are expressed as structured queries or concise summaries. Refine hypotheses iteratively. The agents can refine and expand upon initial hypotheses based on feedback and initial retrieval results, creating a more comprehensive search strategy. How AHG improves retrieval precision. By generating hypotheses before retrieval, AHG significantly improves precision through several mechanisms. Targeted queries. Hypotheses are translated into specific and targeted queries, minimizing the retrieval of irrelevant information. Contextual understanding. Agents consider the context of the query, leading to more relevant and nuanced hypotheses. Exploration of related concepts. AHG encourages the exploration of related concepts and perspectives that might be missed by traditional keyword search. Reduce noise. By focusing on pre-generated hypotheses, the system avoids being overwhelmed by irrelevant matches triggered by ambiguous keywords. Our research and development. Our current research focuses on agent architecture, developing robust and efficient agent architectures optimized for hypothesis generation. Hypothesis evaluation, creating metrics and methods for evaluating the quality and relevance of generated hypotheses. Integration with retrieval systems, seamlessly integrating AHG with existing search engines and knowledge bases. Real-world applications, exploring the application of AHG in diverse domains such as scientific research, legal discovery, and customer support. We are committed to pushing the boundaries of information retrieval and believe that Agentic hypothesis generation holds immense potential for delivering more precise, relevant, and insightful search experiences. Stay tuned for updates on our progress. The evolution of vector search in the age of Agentic AI. Vector search, traditionally a powerful tool for similarity matching and semantic retrieval, is undergoing a profound transformation fueled by the rapid advancements in agentic AI. As AI agents become more autonomous, capable of complex reasoning, planning, and action, the demands on vector search systems are escalating. From static similarity to dynamic contextual understanding. Historically, vector search focused primarily on identifying items with similar embeddings. However, agentic AI requires a far more nuanced understanding of context. Modern vector search solutions are evolving to incorporate contextualized embeddings, moving beyond static representations to dynamic embeddings that adapt based on the specific query, user profile, and real-time environment. Hybrid search techniques, combining vector search with keyword search, graph databases, and other knowledge representation methods to leverage both semantic similarity and structured knowledge. Explainability and traceability, providing insights into the reasoning behind search results, allowing AI agents to understand why certain vectors were deemed relevant, crucial for trust and debugging. Integration with memory and knowledge graphs, using vector search to quickly access and retrieve relevant information from vast internal and external knowledge sources, enriching the agent's understanding and decision-making. Agentic AI driving innovation in vector search. The emergence of agentic AI is not just a beneficiary of vector search, it is also a driving force behind its innovation. AI agents are being used to automated embedding optimization, train and fine-tune embedding models continuously based on agent feedback and usage patterns. Adaptive indexing and partitioning, dynamically adjust indexing strategies to optimize for specific query patterns and data distributions encountered by agents. Real-time relevance feedback loops, learn from agent interactions and user feedback to refine search algorithms and improve the accuracy of results. Looking ahead. The future of vector search in the age of agentic AI promises even more sophisticated capabilities. Expect to see personalized and proactive search, vector search systems that anticipate the needs of AI agents and proactively surface relevant information. Federated and decentralized vector search, allowing agents to securely access and query vector databases across multiple organizations and data silos. Integration with multimodal data, handling vector embeddings derived from text, images, audio, and video, enabling agents to reason across diverse data sources. By embracing these advancements, we can unlock the full potential of agentic AI and build intelligent systems that are more adaptable, efficient, and trustworthy. How Agentic RAG transforms supply chain management intelligence. In today's volatile global landscape, supply chain management, SCM, demands more than just reactive analysis. It requires proactive intelligence, anticipating disruptions, and optimizing performance in real time. Agentic Retrieval-Augmented Generation, RAG, is emerging as a game-changing technology, transforming SCM intelligence by enabling businesses to 1. Unlock deep insights from diverse data silos. Traditional SCM intelligence often struggles with fragmented data residing across disparate systems, ERP, CRM, SCM platforms, external market feeds, etc. Agentic RAG overcomes this hurdle by intelligent data retrieval. AI-powered agents can autonomously search and retrieve relevant information from across all connected data sources, regardless of format or location. Unified knowledge graph construction. RAG models build a comprehensive knowledge graph that connects entities, relationships, and events within the supply chain ecosystem. Contextual understanding. The system understands the context of each query and delivers only the most pertinent information, avoiding information overload. 2. Proactive disruption prediction and mitigation. Agentic RAG goes beyond reporting past events, it actively predicts potential disruptions and recommends mitigation strategies. This is achieved through real-time monitoring, continuous monitoring of news feeds, social media, and internal data streams for early warning signals of disruptions, example geopolitical instability, weather events, supplier financial distress. Predictive analytics, leveraging machine learning models to forecast potential impacts on supply chains based on retrieved information and historical patterns. Automated risk assessment, automatically assessing the probability and severity of identified risks, enabling prioritization of mitigation efforts. Recommended actions, generating actionable recommendations for mitigating disruptions, such as identifying alternative suppliers, rerouting shipments, or adjusting inventory levels. 3. Enhanced decision-making and optimization. By providing readily available, contextually relevant insights, Agentic RAG empowers SCM professionals to make faster, more informed decisions, leading to significant optimization across the supply chain. Improved demand forecasting, enhanced understanding of market trends and consumer behavior for more accurate demand forecasting. Optimized inventory management, real-time visibility into inventory levels and demand patterns, minimizing holding costs and preventing stockouts. Streamlined logistics and transportation, optimizing routes, carriers, and modes of transportation based on real-time conditions and predictive analytics. Enhanced supplier collaboration, fostering better collaboration with suppliers through improved communication and data sharing, leading to greater efficiency and responsiveness. 4. Personalized and adaptive intelligence. Agentic RAG can be tailored to the specific needs and roles of individual users within the SCM organization, providing personalized intelligence that is constantly learning and adapting. Role-based dashboards, customized dashboards that display the most relevant information for each user's specific responsibilities. Adaptive learning, the system learns from user interactions and feedback, continuously improving its accuracy and relevance over time. Proactive notifications, personalized alerts that notify users of critical events or potential risks that require immediate attention. By embracing Agentic RAG, organizations can transform their SCM intelligence from a reactive reporting function to a proactive, strategic asset, driving greater resilience, efficiency, and competitiveness in today's dynamic business environment. Managing state in complex multi-turn Agentic RAG. Building robust and effective Agentic RAG, Retrieval-Augmented Generation, systems, especially those designed for complex, multi-turn conversations, requires careful management of state. State encompasses all the information that the agent needs to remember about the ongoing interaction, user preferences, retrieved documents, and the agent's reasoning process. Poor state management leads to inconsistent responses, forgotten context, and ultimately, a frustrating user experience. Why is state management critical? Contextual understanding. In multi-turn dialogues, the agent must retain context from previous turns to understand the user's current intent and provide relevant information. Maintaining user preferences. Remembering user preferences, example preferred language, level of detail, allows for personalized and efficient interactions. Tracking retrieval history. Understanding which documents have already been retrieved prevents redundant searches and ensures the agent explores new and relevant information. Orchestrating agent actions. Managing the agent's internal state allows it to plan and execute complex actions across multiple steps, such as querying multiple data sources or performing intermediate calculations. Ensuring coherence. State enables the agent to maintain a consistent persona and reasoning style throughout the conversation. Key strategies for effective state management. Several strategies can be employed to manage state effectively in complex agentic RAG systems. Conversation history. Storing a complete or summarized history of the conversation allows the agent to refer back to previous turns. Techniques like sliding window buffers or summarization models can help manage the length of the history. User profiles. Maintaining user profiles that capture preferences, demographics, and past interactions enables personalized and targeted responses. Session data. Storing session-specific information, such as current tasks, retrieved documents, and intermediate results, ensures the agent can resume conversation smoothly. Knowledge graphs. Using knowledge graphs to represent entities, relationships, and contextual information provides a structured way to reason about the conversation and retrieve relevant knowledge. Memory networks. Employing memory networks, such as LSTMs or transformers, allows the agent to learn and retain relevant information from the conversation history. External databases/stores. Storing state information in external databases or key value stores provides persistence and scalability for handling a large number of concurrent users. Challenges and considerations. Despite the available strategies, state management in agentic RAG systems presents several challenges. Scalability. Managing state for a large number of concurrent users can be computationally expensive and require significant infrastructure. Privacy. Storing user data raises privacy concerns and requires careful attention to data security and compliance with regulations. Complexity. Implementing and maintaining state management logic can be complex, especially for systems with sophisticated agent behavior. Context length limitations. Many language models have limitations on the length of the input they can process, requiring strategies for summarizing or compressing conversation history. Maintaining consistency. Ensuring consistency between different state components, example conversation history, user profile, retrieval results, is crucial for preventing errors and inconsistencies. Best practices. To mitigate these challenges, consider the following best practices. Choose the right storage solution. Select a storage solution that meets the scalability, performance, and security requirements of your application. Implement data anonymization and encryption. Protect user privacy by anonymizing sensitive data and encrypting state information. Design for modularity and maintainability. Structure your code to make it easy to understand, modify, and debug the state management logic. Regularly monitor and optimize performance. Track the performance of your state management system and identify areas for optimization. Implement robust error handling. Handle potential errors gracefully and provide informative error messages to users. By carefully considering these strategies, challenges, and best practices, you can build agentic RAG systems that provide a seamless, engaging, and informative user experience. The role of JSON schema in agentic RAG tool calling. In agentic RAG, Retrieval-Augmented Generation, systems, the ability for the agent to effectively call tools is crucial for solving complex tasks. JSON schema plays a pivotal role in enabling this functionality by providing a standardized and machine-readable way to define the inputs and outputs of these tools. Why JSON schema for tool definition? Standardization. JSON schema provides a universally understood format for describing data structures. This ensures consistency and interoperability across different tools and agent platforms. Validation. Before a tool is invoked, the agent can use the JSON schema to validate the arguments it intends to pass. This prevents errors caused by incorrect data types, missing fields, or invalid values, leading to more reliable tool execution. Documentation. JSON schema acts as a self-documenting description of a tool's interface. This makes it easier for developers to understand how to integrate new tools into the agentic RAG system. Automatic UI generation. JSON schema can be used to automatically generate user interfaces for interacting with tools. This can significantly speed up development and improve usability. Type safety. By defining the expected data types for inputs and outputs, JSON schema promotes type safety and reduces the risk of runtime errors. Enabling agent reasoning. The structured nature of JSON schema allows the agent to reason about the capabilities of different tools and select the most appropriate tool for a given task. The agent can examine the schema to understand the required inputs and the expected format of the results. How JSON schema works in agentic RAG tool calling. Tool definition. Each tool is defined with a corresponding JSON schema that specifies the expected input parameters, including their names, data types, descriptions, and constraints, and the format of the output it will produce. Agent reasoning. When the agent needs to call a tool, it retrieves the JSON schema associated with that tool. Input generation. Based on the schema, the agent formulates the input payload for the tool, ensuring it conforms to the defined structure and data types. Validation. Optional. The agent can validate the generated input payload against the JSON schema to prevent errors. Tool invocation. The agent invokes the tool with the validated input payload. Output parsing. After the tool executes, the agent parses the output and validates it against the JSON schema, if specified for the output. Knowledge integration. The agent integrates the parsed and validated output into its knowledge base or uses it to generate a response. Example, JSON schema for a search tool. Type, object. Properties. Query. Type, string. Description, the search query. Min length, 3. Number _ results. Type, integer. Description, the number of search results to return. Default, 5. Minimum, 1. Maximum, 10. Required. Query. This example illustrates how a simple search tool can be defined using JSON schema. The schema specifies that the tool requires a query of type string and accepts an optional number underscore results parameter of type integer. The agent can use the schema to ensure that it provides valid input to the search tool. Conclusion. JSON schema is a critical component of robust and reliable agentic RAG systems. By providing a standardized way to define tool interfaces, it enables agents to reason about tool capabilities, validate input and output, and ultimately perform more complex and sophisticated tasks. Why Agentic RAG is the foundation of AI-driven market research. In today's dynamic market landscape, staying ahead requires more than just data, it demands actionable insights derived swiftly and accurately. Agentic Retrieval-Augmented Generation, RAG, is revolutionizing market research by providing the foundation for AI-driven analysis that surpasses traditional methods in speed, depth, and strategic value. Unlocking deeper insights with intelligent agents. Traditional market research often relies on manual data gathering and analysis, leading to significant time lags and potential biases. Agentic RAG overcomes these limitations by employing intelligent agents that proactively seek information. Agents are programmed to autonomously search diverse sources, including market reports, social media trends, competitor websites, and customer reviews, ensuring comprehensive data coverage. Contextually understand data. Unlike simple keyword searches, agents leverage natural language processing, NLP, and contextual understanding to identify relevant information even when it's expressed in nuanced or indirect language. Dynamically adapt to new information. As the market evolves, agents continuously learn and adapt their search strategies, ensuring that research remains current and relevant. RAG, bridging the gap between information retrieval and generation. Retrieval-Augmented Generation, RAG, is the crucial component that transforms raw data into actionable insights. It works by retrieving relevant information. Based on specific research questions or objectives, the agent retrieves the most pertinent information from its vast knowledge base. Augmenting generation with context, the retrieved information is then used to augment the AI's generation capabilities, enabling it to produce insightful reports, strategic recommendations, and personalized